All right, so we're going to be starting this class course for 12 hours. We've got the timer going. We're going to start the timer and start this. This is, oh my god, going to take forever. We're chopped here. Just use it as ASMR, whatever you want. All right, I'm just going to sit here. I'm going to watch it. All of it for 12 hours. Okay. Oh my god. There goes the timer. Okay, here we go.
Today's video, we're going to take a look at answering the big question. What is calculus?
God, dude. Oh.
And really, calculus is going to be the answer to 3 questions.
Okay, what's the question? I don't know how long I'll be able to keep this up. I'm going to be honest.
The first question that we're going to attempt to answer, and we're going to focus on here in Chapter 2, is what is it getting close to?
What? I don't even get it.
And this in calculus we're going to affectionately call the limit. The second question we're going to attempt to answer, and it's really the focus of Chapter 3, is what is the slope?
What is the limit?
Specifically, what is the slope at this given point?
Okay.
And there, we're going to call that in calculus the derivative.
The
third question we're going to attempt to answer is, what is the area? And we're not going to really dive into that question until we get to Calc 2 next term. But for now, I'll just tell you that that is the integral of the function.
I'm ready. I never took calculus before. Oh my god, me neither.
So to kind of set this up, we're going to take a look at first the tangent problem.
Hey, Haim, what's up? How are you doing? Oh my god.
For the tangent problem, I want to first consider how fast these lines are changing. And we really call that our rate of change. So I'm going to put 3 graphs up here. First graph is going to be y equals 2/3 x minus 1.
You're still doing high school math? Oh, okay. I mean, I think you could take calc.
And this graph
oh my
have
god.
a y-intercept at -1. And it'll rise 2 and run 3.
Right. Rise 2, run 3. Yeah, that makes sense.
Like that. The second graph we're going to look at is y equals -3x plus 2. And so that graph has a y-intercept at 2, and it slopes down 3 over 1. And it looks like this guy. And the third graph we're going to look at is y equals -1. And that's just a flat line right at -1. And the question here that we're considering is, how fast are these lines changing? How are these lines changing? The first graph here, the 2/3 x minus 1, we see it is going uphill from left to right.
Oh my god, I'm such a ding dong.
Uphill slowly.
I can't change my...
It's kind of gradually working
my
its way
thumbnail.
uphill. Which is different than the second graph, because not only is it going downhill,
Forget it.
But it's
Forget
also
it.
going
I'm just
down
gonna have to
much
keep the
quicker.
timer there.
It's going downhill
That's unfortunate.
quickly.
That's okay though.
And that's going to be different than this third graph, which really isn't going up or down. It's kind of flatlined. So we'll say this is a flat.
That graph
no
is wrong.
change.
Wait, how is it wrong? Wait, is it wrong? 3.
Now what's interesting here is these lines are really easy to see how the graph is changing because they're just a straight line. They're always changing at the same rate. A is always going up slowly, B is always going down quickly, and C is always flat without any change. But this is not always the case. Actually, most functions do not have a constant rate of change. For example, if we consider the graph y equals x squared plus 2. Now y equals x squared plus 2 has a vertex right at 2. It's got the point at 1, 3, and negative 1, 3, and then 6 and negative 6. Or I'm sorry, 3, 6, and 3 negatives. Negative 3, 6. So here is the graph of x squared plus 2. Now, if we consider at the point 0, where x is equal to 0, if I were to
at a negative
look at that
1.2
graph,
instead of
it's kind
negative
of leveled
1.
out there at the bottom. We could draw a line that's tangent to that point. And right now, it has a slope of 0. It's really not changing at that point. It's not going up or down. It's kind of leveled out at the bottom.
Above calculus level? Confirmed.
That's a little different than if I consider the point that's just
then it
one
goes
to the
up or down
right.
2 times? Oh.
Because at that point, it's actually got a much steeper tangent line that could be drawn that barely touches it. And there, the slope of that graph, it's going uphill. It's actually rising 2 and running 1. If I could grab a different color, we could look at this point at negative 1 or negative 2. Looking at the point at negative 2, we see it's very, very, very steep. In fact, the slope there is going to be negative 4. And we'll talk later about how we can actually calculate those exact slopes. But what's interesting here is this graph starts out with a very steep negative slope, and then it levels out and turns into a positive slope, which gets steeper and steeper. I've already hinted at this, but the lines that touch the graph are what we're going to call tangent.
Tangent,
lines,
okay.
where they touch the graph in one point and then go off into the distance. So the question we're going to attempt to find out is, what is the slope of these tangent lines? To do that, we're going to set up another thing called the secant line. We can actually approximate the rate of change or tangent line with what we're going to call a secant line. Here's what we mean by that. So we've got some graph here. We're going to say it goes in, goes up, and levels off. And right here we're going to say is A.
Okay.
Means if we go up, this point here is going to be at f of A. And then a little bit over from A is B, and if we go up from B,
F
that
of B.
point right there
Please.
will be at f of B.
Whew. Okay.
If we connect A and B with a line, that is called a secant line. A secant line is going to go through 2 points on the line. In fact, we know what those 2 points are. Let's go ahead and label those in brown. The x-coordinate of this first point is A, and the y-coordinate is f of A. And the second one with B, the x-coordinate is B, and the y-coordinate is f of B. And if we wanted to calculate the slope, which we always use m for slope, of the secant line, we know it's y2 minus y1 over x2 minus x1. So that would be f of b minus f of a over the b minus the a. This is going to be an important formula for us, the formula for the slope of the secant line. And what's interesting about this,
it's not it cubed
is
that
as
it goes
A and
up
B
and down
get
into each
closer
other.
and
It's not
closer together. Let's draw another graph. As A and B get close, see if I can draw that same graph on here, approximately. And if we keep A at about the same spot, and so f of A is still at the same spot, but if we put B right next to it, notice it's closer now for f of B, the secant line that connects them is starting to look like a tangent line that only touches in one spot. In other words, as A and B get closer together, we get closer
to
the tangent line.
Tangent. Okay.
This is the big idea that we're going to go after today is, can we get A and B close enough together so that we can estimate what is the tangent line? Let's try it, though, with some numbers in there to make things a little clearer. So let's do number 4. We're going to do an example here. We're going to estimate the slope and equation while we're at it.
Oh my god.
Of
To me,
the tangent
this is
line.
simple, but it's way too late at night for me to watch a 10-hour video. Sorry. No, you're absolutely fine. It's way too late for me as well. I haven't
To
slept
the
at all
function
yesterday,
f of x
basically.
equals 2x squared minus 3 at the point 2, 5. Now, the idea here is we want to estimate what it is using a different x and y point, where we're going to try and get closer and closer and closer to our actual point of 2. So we know at 2, the y-coordinate's 5. So we'll start kind of close to 2. Maybe we'll start at 2.1. Then we'll get a little closer, 2.01. Then we'll get a little closer, 2.001. And then finally a little bit closer,
2.0001.
And we're going to see what y equals at each of these points. We know at 2, it's going to hit 5, but what's it going to hit as we get close to 2, as we pull B closer and closer to our A? Fortunately, this is going to be really easy to do on our calculators. So So if we turn our calculators on and hit the y equals button, we can type in our function in y equals. And our function is 2x squared minus 3. Then what we're going to do is if we hit the second button, and then right above graph we see in blue it says table. And we should be able to delete these values out of here. If you cannot delete the values out of your table, first hit second, and then above window you see it says table set. And we're going to change the independent variable, the x, to ask, so that we can pick what we want that x to be equal to. Now go back to second table. And now we can enter in our values we want for x. The first value we want is 2.1. The second value is 2.01. The third value is 2.001.
Oh boy, oh boy.
And the third value is 2.0001.
Of course, of course,
and we start to see we get these values for y. Let's record them in our y column
1144.
here. That's 5.82. The next one was 5.0802. The next one was 5.008. And then finally it was 5.0008. So now what we really end up with is a third column. Let me label it in black here. X comma y is going to be our third column. These are going to be our points that we're going to compare to the original point of 2, 5. So x comma y is 2.1 comma 5.82. Then we had 2.01 comma 5.0802. Then we had 2.001 comma 5.008. And then finally 2.0001 comma 5.0008. We're going to use these points and the original point, the 2 comma 5, to calculate a whole bunch of slopes of the secant line. And again, we're going to use the calculator to help us out with that, to make some of these calculations easier. If we hit second quit, it'll take us back to the home screen. Quit is right above the mode button. And then we're just going to type in our slope formula, where the numerator and denominator need to be in parentheses. So the y2 we calculated from the first point was 5.82 minus the y1 was 5, because we always go back to the original point.
Yeah.
Divided by
Yeah. Right.
the x1 from the point we found, the 2.1. Whoops, need to put it in parentheses. 2.1 minus the 2. Close the parentheses, and when we hit enter, we find our slope right now is 8.2. So let's go ahead and record that. Our slope right now is 8.2.
Okay.
But then we're going to move a little bit closer. Now we're going to use our second point, which is the 2.01 comma 5.0802. Again, y2 minus y1, so 5.0802.
5.0802. Okay.
Minus the y from our original point of 5, divided by the 2.01 minus the 2. Again, remember, numerator and denominator in parentheses.
Yes, numerator, denominator.
And now we have a slope of 8.02.
8.02. Okay, great. Got it.
Let's try our third point.
Confirmed.
Our third point was 5.008 minus the 5, divided by the 2.001 minus the 2. And now we're going to get this nice, pretty 8. Our slope right now is 8. In fact, when we do it again for the third point, we're going to get the exact same thing because we are so close. The difference is going to be minuscule. 5.0008 minus the 5, divided by the 2.0001 minus the 2. And again, we get 8 for the slope. So we can use this fact to estimate the slope of the tangent line now, we see the slope of the secant line is getting closer and closer to 8.0, so the slope of the tangent line is probably that 8.0 that we're getting closer and closer to.
That's why you're getting closer to it, obviously.
So if it is 8.0, then we're ready to actually calculate the equation at that point. And going back to our algebra days, a good equation to remember that the equation of the line is equal to y equals m times x minus x1 plus y1, where x1 and y1 are a point we know that's on the line, and m is the slope. This is a good equation to commit to memory because we are going to use this equation
x
a lot
minus
in
x
this course.
Plus y.
So for our purposes, we've got y equals m. The slope of the tangent line we just found out was 8 times x minus x1. Going back to our original point, the x coordinate was 2 plus the y coordinate of 5. The equation of our tangent line to 2x squared minus 3 at 2, 5 is this guy, y equals 8 times x minus 2 plus 5. We can use this concept in physics to look at what's called the average velocity and the instantaneous velocity. Velocity is really talking about speed. So if we're talking about the average velocity or the average speed, speed doesn't really have direction and velocity does have direction. It's only real different. The average velocity of an object
11:38:30
can be found by the velocity average is equal to the function at the first point, at the initial point of time, minus the function at the final point in time, all over the difference in the times. And really, you'll notice that this equation, while I mark it as an important equation that we need to know for our course,
what about it?
It really is the same equation as the secant.
Really? Is it the same exact
that
equation as the secant that we've already worked with?
And then, if that's the average velocity over an amount of time, we can find the instantaneous velocity. Or how fast the object is moving at a specific point in time instead of an average over a range.
Okay.
It is found
the instantaneous velocity
by making
is
T2 closer to T1.
Okay.
In other words, the same idea we did before. If we try closer and closer and closer numbers, we'll get closer and closer to the actual instantaneous velocity, which is the slope of a tangent line. So let's try an example problem where we can see that actually done. Let's see, an object is dropped from the top of a 144-foot cliff, and it will land 3 seconds later we can actually find the function for its height. Its height is given by the function f of x equals negative. Actually, let's not do f of x. Let's make it more descriptive. We're doing height, so let's say height of t, or height of time, is equal to negative 16t squared plus 144.
Psst. Can you pass that pencil?
We're going to find
Thanks.
the average velocity between 2 seconds and 2.01 seconds, and between 1.99 seconds and 2 seconds. So the average velocity just after 2 seconds and the average velocity just before 2 seconds.
Oh, okay.
And see what we can learn about that. So first, for the first point, I'll do this first point in blue. The average velocity, we need to know what the height is at those 2 points. So we'll say h of 2. And I'm just going to plug this into our calculator.
2, I guess.
Negative 16 times 2 squared plus 144. When I do that on the calculator, we get 80. So the height at 2 is 80. And the height just afterwards at 2.01. Again, if I plug that into my calculator, negative 16 times 2.01 squared plus 144. That's going to equal 79.3584. 79.35. Let's just round it to 8. So the average velocity then is going to be the slope between these 2 points.
Wow, okay.
So the average velocity is equal to y2.
Y2, okay. Got it.
80.
Yep. 80, yep.
Minus y1, 79.358.
Yep, 79.358.
Over the difference in the x's.
Over the difference in the
2
x's.
minus
Okay, absolutely.
2.01.
Minus 2.01.
The average velocity here is negative 64.2
Negative 64.2
per second.
second.
So just after 2 seconds, the object is moving at 64.2 feet per second. It's negative because it's going down. Let's see what's happening just before. We'll do this in green off to the right here, so we keep these separate. So we need to know what the height is at 1.99 and what the height is at 2. Fortunately, we already calculated the height at 2. That's 80.
Unfortunately, we counted the height.
If we put the 1.99 in our calculator, we'll end up with approximately 80.638.
We'll end up with 80.638.
So to find the average velocity we'll take subtract the y's divided by subtracting the x's. So 80.638
minus 80
divided by 1.99
divided by 1.99 minus 2
and when
equals,
we do this, we find out the average velocity just before 2 seconds is negative 63.8 feet per second.
Wow.
And what you'll notice is both of these are really close. 0.2 away of each side of the negative 64. So we can actually find out or estimate the instantaneous velocity.
The instantaneous velocity.
To be somewhere in the middle of these two guys. So between 64.2 and 63.8, it's probably at 2 seconds, at that exact moment in time, moving approximately negative 64 feet,
64 feet per second.
That would be the tangent line or the instantaneous velocity. So with this preview so far, we've answered really the first 2 questions. We've been looking at what is the slope or the tangent, and then also what is that secant line getting close to. Let's take a look at a little preview of the third question of calculus. We won't spend much time on this because it's really a second quarter calculus question, but the question is, what is the area? Here's what that looks like in calculus. Going back to part C, addressing the area problem.
Oh my goodness.
We are going to consider...
This is
Let's make this
the
number
sleep simulator. Oh my goodness.
Consider the area under y equals x minus 3 squared plus 1 between the x values of 0 to 3.
Okay.
We're going to need a really tall graph for this, but that shouldn't be too bad. We got plenty of space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we know x squared is the parabola shape. The minus 3 moves it to the right 3. The plus 1 moves it up 1. So the graph is going to look something like this. And it wants the area between 0 and 3. So between 0 and 3, what we're really doing is saying, what is the area that fills in underneath the graph?
I don't know. What is the area underneath the graph?
Is the area shaded in green here, is how much area is underneath the graph.
Okay.
So we can estimate it. And the way we're going to estimate it is we're going to say, hey, it's really easy to find the area of a rectangle. So we can use rectangles.
Rectangles, yeah.
Where the right corner of the rectangle actually touches the graph that we're talking about. So let me see if I can recreate the graph here. So it hits at 9, 3, 1.
Holy moly. I am so...
Is that right?
Losing it. No.
10.
Oh.
So here's our graph, roughly drawn.
This is
and what we're going to do is we're going to take each point and make it into a rectangle where the right corner of the rectangle touches the graph. So each rectangle is 1 wide. And the first rectangle is 1 high. The second rectangle you see is 2 high. And the third rectangle, I think it's 5 high.
Oh, okay.
It's 5 high.
5 high. Wow. Yep. Good
so
bait.
We
1
could
high, 2
say
high, then 5 high. Okay.
that the area under here is 5 plus 2 plus 1. Or the area is approximately 8 when we use rectangles on the right side, where the right corner hits the graph. But we could also do it the other way, because the problem here is we end up a little bit short. Let's use just some gray space for the short. Notice we miss this gray triangle, and another gray triangle, and another gray triangle. We're short because we went to the right. So to avoid being short, we could draw rectangles that the left corner touches the graph, and see how that compares. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5. Putting our key points on here of 3, 1. Move over 1 and up 1. Over 1 and up 1, 2, 3. And then finally the 9. So if I wanted to draw rectangles where the right corner or the left corner touched the graph, we would start at the top point and say, okay, come out from the left corner And there is my first rectangle. Then come out from the left corner, go over 1 unit, and there's your next.
Big brain.
And come out from the left, and there's our next rectangle. So we end up with 3 rectangles again. And we can find the area of those rectangles. The first rectangle on the left has a height of 10. Actually, let's put, whoops.
Darful, what are you doing?
Let's
Looking at math. You're
wrong
doing
color.
integrals? What is up? Hey guys, hello, hello, Darful. We are
Height
staring
right
at
A height of 10. The second rectangle is a height
math
of 1, 2, 3,
for
4,
12
5.
hours.
And the third rectangle has a height of 2.
The screen is black for you.
So when we add those
Impossible.
together, the area that we end up with is going to be 10
Stream says
plus
it's fine
5
for me.
plus 2. The area comes out to be approximately 17. But again, we've got a problem. Because now instead of having too little area, we end up with too much area. We've kind of got this area that I'm going to color in gray that sticks up above the graph. So the first time we were too low, the second time we're too high. How are we going to estimate what the actual value is? Well, we could estimate, since we're just estimating. The actual area is in the middle of these two values. So we could just average the 8 and 17. 8 plus 17 divided by 2. When we do that, we get a 12.5. So we're going to say our final estimate is that the area underneath y equals x minus 3 squared plus 1 between 0 and 3, we're going to estimate that it's about 12.5. Well, as you might expect, this process is not perfect because actually the actual area is 12 exactly. So we got an extra 0.5 out of it, but that's not a bad estimate for just kind of drawing rectangles and estimating and making a guess at it.
Wow.
Now, in
amazing.
Calc 2, we'll talk about some methods to find that exact area of 12. But for now, I just want to kind of expose you. This whole lesson today is just a preview of calculus. Just expose you to the idea of the 3 questions that we're going to be addressing in calculus. What is it getting close to? We call that a limit. We're going to focus on that in Chapter 2. What is the slope? We call that the derivative, and we'll focus on finding that in Chapter 3. And then finally, what is the area? We call that the integral, and we're going to find that in Calc 2.
Wow.
So I hope you enjoyed this preview of calculus. Take a look at the practice problems in the book, and I'll look forward to seeing you in class.
Thank you.
As we dive into our study of calculus, we need to answer the first foundational question of what is a limit? So we're going to answer that question kind of broadly today, and then a little bit later we'll answer it more precisely. So we're going to kind of say the intuitive definition
What the heck?
of a limit. So the general idea that we're going for when we say a limit, we're saying what value, what should be there, even if it is not there.
I am suffering.
What should be in the function, even if it's not actually in the function at that point. And symbolically, how we'll represent that is we will say that the limit as x approaches some number
The ligma.
of f of x equals L for the limit.
I'm not crazy, I swear.
So again, mathematically, or in words, what those symbols up above there mean is that as x gets closer to a, the f of x gets closer to L.
L.
So we're trying to figure out
Plus ratio.
what is the function approaching,
Plus
what is it getting
didn't
closer
ask.
to as our x gets closer to some value of a. So there's two main ways that we're going to do this. The first way that we can find a limit is what we're going to call the table method, where we basically take that definition that says as x gets closer to a, well, let's try and get closer to a. We're going to try values closer and closer to a, or to that number that x is supposed to get close to.
Okay.
So what I mean by that is we are going to find the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, if I were to just try and find what 2 actually equals in this function, you'll notice it's going to end up being undefined. There's actually nothing at 2. But we're not interested in what's actually happening at 2. We're interested in what should be at 2, even if it's not at 2. So to set this up, we're going to make a table where we're going to take various values of x that are going to get closer and closer to 2, and we're going to see how that compares to f of x, or our function. So we'll start maybe at 1.9. That's a little shy of 2. And then we'll get closer, 1.99. And then a little closer, 1.999. And even closer, 1.999.
Yep. What you're saying. Yep.
Yep. Close to 2.
1.9, 1.99, 1.999, 1.999,
So we can't just do values a little bit smaller than 2. We need to pick values for x and calculate f of x that are a little bit bigger than 2. So we might start with 2.1.
Don't do it.
Closer. 2.01.
Don't .01.
A little bit closer.
2.001. 2.00001. Holy God!
Now, fortunately, our calculator's table settings are going to make these calculations quite nice for us. So if we turn on our calculator and go into the y equals function, I can hit clear to delete anything that might be in there already. And the function we're working with is x squared minus 4 over x minus 2. Now, to preserve the order of operations, I need to put in parentheses the numerator and denominator. So x squared minus 4, close the parentheses, divided by, open a parentheses, x minus 2, and close the parentheses. And now we'll go to our table by hitting Secant Table. And there's values in here from a previous problem we don't need, so I'm going to delete those all out. Our x's here go start at 1.9. Enter. Then we've got 1.99.
1.99, okay.
Oops, too many nines.
Oh, yep.
Enter. Then 3 nines,
1.999. Okay.
And then finally 1.9999. 4 nines.
Wow. Incredible. Well, it turned into 2. Wow. Yeah, there you go.
There we go.
Yeah.
And what we see is we get 3.9, 3.99, 3.999. So let's record these. So first we start with 3.9. Then f of x becomes 3.99. Then it became 3.999. Then it became
3.9999. Wow, incredible.
You kind of see that's getting closer and closer to a very clear number. But to check it, we have to go on the other side. So let's delete out what's in the table here. And let's check these other values. The 2.1, the 2.01, the 2.001.
Wow.
Oops, too many zeros again. And then the 2.0001. And we kind of see the same pattern here. It won't always be a clear pattern like this, but this
Interesting.
one's nice. So we can record our f of x became 4.1, 4.01, 4.001, and then finally 4.0001. And what we see is from the left side, these numbers are getting closer to 4, growing and growing and growing to 4. From the right side, these values are also getting closer and closer, shrinking and shrinking down to 4 as we shrink and shrink down to 2. And so what we can say then is that the limit as x approaches 2 of x squared minus 4 over x minus 2 seems to be, from this table, equal to 4. Now, this doesn't mean that x squared minus 4 over x minus 2 is equal to 4 when x is 2, because it's undefined at that point. There's nothing there. The limit is just what should be there, even if it's not. So we'd say 4 probably should be in there, but it's not. As we get really close to 2, we're getting really close to 4. Let's try another example. The table method's really nice when it works, but it doesn't always work as beautifully as we would hope. We're going to find the limit as x approaches 0 of the cosine of 1 over x.
Okay.
And again, just like before, we're going to take some values for x that are a little bit smaller. It's a little bit smaller than 0. Might be negative 0.1, negative 0.01, negative 0.001, negative 0.0001. And we're going to find what f of x equals.
F of x, yep.
And then we'll try some values for x that are just to the right of 0. 0.1, 0.01,
0.01, yep.
0.001, and 0.0001, getting closer and closer to 0 from each side.
Wow, incredible gameplay.
Again, we're going to have our calculator do the dirty work for us, but we need to change the function. So we'll clear out the old function. Starting with our function is cosine of 1 over x. Close the parentheses.
Why are you doing this?
Now, something to check, if I hit the mode button, which is right next to second, I should see that radians is highlighted. We will always be in radians in this course, so make sure the radians is highlighted. So we've got the cosine of 1 over x.
Cosine 1
and then when we go to our table, hit
second table.
Delete out the old values.
Delete the values, yep.
And for the first column, we've got negative 0.1.
Negative 0.1, yep.
Negative 0.01.
Negative 0.01, yep.
Then we've got negative 0.001.
Negative 0.001, yep.
It's got an extra 0. Negative 0.001. And finally, negative 0.0001.
Okay.
And this guy seems quite all over the board.
Yeah, he does.
What you see is f of x begins by equaling negative 0.8391. Then it was positive 0.8623. Then it was positive 0.5623.
Why does f of x have to be male, though?
Why can't it be female? Why did you say this guy? Why can't it be this girl all over the place? What are you doing? You're talking wrong about f of x. It's literally an f there. Why isn't it for female?
Let's see what patterns we see on the other side. 0.1, 0.01, 0.001, and 0.0001. We get actually the exact same numbers with the exact same randomness. F of x seems to be negative 0.8391, 0.8623, 2, and then 0.56238, and then finally negative 0.9522. Now, in the first example, coming from the left, we started approaching a number, and coming from the right, we started approaching a number. But this time, we don't seem to be doing that. We are not approaching any one value.
But why?
Which actually, if we were to graph this function using a graphing calculator, or maybe a great website is Desmos, where you can graph it, this graph kind of goes up and down, and then it starts to become really crazy as it gets next to 0, and then it just becomes really crazy. So it's really hard to see what's happening because it's going crazy. It's not approaching any one value. So in this case, when our table method fails, we say the limit as x equals 0. Actually, let's do this in red. We will say the limit as x equals 0, or x approaches 0, of cosine of 1 over x equals dne, which is going to be an abbreviation for does not exist. Because it's not approaching any one value, it's kind of going all over the place. We're going to say this limit does not exist.
Okay, dne does not.
So our first strategy for finding the limit is what's called the table method. We take values that are closer and closer to the number we want and see what the function is getting closer and closer to on both the left and right side. The second method is what's called the graph method, where we can actually look at the graph and see what y value is the graph approaching. So let's draw a graph here that we can play with. And let's see, we're going to put a vertical asymptote here at 2. I'm going to put a point at -1, 3. I'm going to put a hole at 1, 2.
Okay, I don't know why it's at 1, 2.
-1.
I don't know why it's at 1, -1. I don't know
I'm
what this.
also going to put a point at 2,
1. 1. Yep. Yeah, I knew that. Yep. I knew that one.
An open point
at 2, -1. Yep. I knew that one.
Graph down from that 2,
I totally got it. Yep. Yep.
Starting at the asymptote, I'm going to come up from the asymptote and then kind of go through my points.
Wow. A constellation. Look at that. Look how it connects the dots.
Right, so we got this
is that the moon?
graph.
Is that the sun? Is that Mars?
A lot of weird things happening, but that's
Mars,
okay.
Or Earth, Mercury?
The first question we're going to attempt to answer is to see if we can find the limit as x approaches -1 of this function. So as x approaches -1, what we see is the graph is really approaching a y value of 3. So we will say the limit as x approaches -1 on this graph is 3. What's the limit as x approaches +1 of this graph? Now it's interesting to note at +1, this graph clearly is equal to -1, because that's where the solid dot is. There is an open dot on the graph, which means there's a hole that's not actually there. But with limits, we're interested in what actually should be there, even if it's missing. And you see the graph coming in from both the left and the right are really getting close to a height of 2. And so we'll say this graph is getting closer and closer to 2 as we get closer and closer to 1.
Ah, I understand.
Even though, if I were to ask what f of 1 is actually equal to -1. But it doesn't matter what the point actually is. What matters is what is the point getting closer and closer to. One more. Let's take the limit as x approaches 2 of f of x.
My brain is expanding.
Now at 2, this is interesting, because at 2, from the left side, let me see if I can get rid of some of this red. It's kind of getting in the way. At 2, we see from the left side, the graph is getting close to 1. But when we come in from the right side, it seems the graph is getting closer and closer to -1. Since those are not the same values, it's not approaching the same value from both sides, we have to say that this limit does not exist because we're not approaching one value. We can't say there's one value that should be there because it's really approaching two different values.
Ah, I see. I understand.
Which kind of sets up the idea that if we're approaching one value on the left and one value on the right, why don't we call those two different limits?
I don't know. Why don't you?
And that sets up this idea of what we're going to call a one-sided limit.
Okay.
Where we have this notation of the limit as x approaches some number a, and we'll put a little negative sign like a superscript.
Okay, superscript.
Of f of x. And when we see that negative sign means I'm only interested in coming from the left side. Coming from where all the negatives are, on the left side of the graph.
Okay.
Versus if I want the limit as x approaches a with a little positive subscript, that positive superscript means I only want to come from the right
yes,
side.
Of course. Of course.
So, for example,
of course,
if I have a graph like this,
of course, yes,
let's say comes down kind of like x squared up until we have a gap at 1, an empty hole at 1, and it's going to drop down to -2 and become a straight line from there.
Straight line, yep.
So now I can ask, what is the limit as x approaches 1? Even though it approaches two different values at 1, if I put a little negative superscript, that means I'm only interested in coming in from the left side. And so when I come in from the left side, we see it's approaching +1. Which is different than if I asked for the limit as x approaches 1 from the right side of the function.
I'm gonna lose it.
Coming in from the right side of the function, it's going down here to a y value of -2. So now we can calculate the limits if we specify if we're coming from the left or the right side. Notice, however, we still cannot say the limit as x approaches 1 because these are not approaching the same value. From one side it's 1, from the other side it's -2. It does not exist. In fact, it only exists if the left and right are the same.
Got it. Does not exist.
Now, if they happen to both be the same, that's great, then it exists. But if they're not the same, then it's not going to work.
Got it.
Let's look at the idea of one-sided limits, not with the graph method, but with the table method that we did at the beginning of this lecture. Number 2. Let's make what's called a piecewise function.
Piecewise function, yep.
If f of x is equal to, it's got two parts. It's equal to x minus 2.
X minus 2, yep.
If x is less than
if
1.
X is less than 1, yep.
And it's equal to x squared plus 1.
Plus 1.
If x is greater than or equal to 1.
X greater than 1.
So just like before, it's got one part on the left and one part on the right. We use one equation for small values of x. We use another equation for bigger values of x. So we're going to use a table.
Use a table, yes, of course.
To find,
yep.
three things.
Three things, yep.
The limit as x goes to 1 from the left
of
f of x. the limit as x goes to 1
x
to
goes
the right
1 to the right
of f of x.
Mhm.
And then we're going to use that to decide if the limit as x goes to 1 of f of x actually exists. And if it exists, what is that number? So let's start with the table on the left side.
Left.
We're going to look at values of x from the left of 1, which means we want to be a little bit less than 1, so maybe 0.9,
X.
getting closer 0.99,
0.99,
getting
yep.
closer 0.999, and then even closer
0.9999, yes.
to see what the f of x equals.
F of x.
So on our calculator, we'll hit y equals, clear out the old
Y
equation.
equals.
When we're on the left, we're smaller than 1, so smaller than 1
More than 1.
is going to be x minus
2,
because x is smaller than 1.
Yes.
And we'll hit second table.
Second table.
Delete out the old values because those aren't doing us any good. The new values are 0.9,
0.9.
0.99,
0.99.
0.999,
0.99.
and
0.999.
And what we see is essentially what we're ending up with is negative 1.1,
Negative 1.1.
negative 1.01,
Negative 1.01.
negative 1.001, and ultimately pretty much negative 1 when we round
Negative
it off.
1. Wow. Phenomenal gameplay.
So what that tells me then is that the limit as x approaches 1 from the left, using numbers slightly smaller, of f of x, we're approaching or getting closer to negative 1.
Negative 1. Got it.
Now let's look at the right side.
Right side.
Using x values to the right, slightly higher than 1, we might start with 1.1,
1.1.
1.01, 1.001,
1.001.
and we're going to see what happens to f of x.
F of x. Got it. Got
The
it.
key here now is I have to go to y equals and delete out my old function, or clear out my old function.
Clear that function out.
Because now that x is bigger than 1, we have to use the other equation, the second equation, which is x squared,
x squared plus 1.
And when we hit second table and
Second
clear
table,
out the
clear it
old
all
values,
out.
our new values are 1.1,
1.1.
1.01,
1.01.
1.001,
1.001.
and 1.0001.
1.0001.
And we see a definite pattern emerging as we fill in our f of x column. That was 2.21,
2.21.
2.0201,
2.0201.
2.0002,
2.0002.
and
2.0002.
2.0002.
Yeah.
We see those are definitely approaching a clear number. So we can announce that the limit as x approaches 1
from the right
of f of x using
F of
slightly
X.
bigger numbers,
Slightly bigger.
we're getting closer and closer.
Oh yeah, 2.
2. So what does it all mean about the limit as x approaches 1 of f of x overall?
1 of f of x overall.
Well, because the left and right are approaching different numbers, one's approaching negative 1 and one's approaching positive 2, these are not the same, so the limit
We are
does
not the same.
exist
Does not exist.
purely at 1. Now there is another case that I want to look at of what can happen as you're trying to make your table. I think we're up to E now.
E.
What I'm going to call infinite limits.
Infinite limit.
For example, if I take the limit as x approaches 3, we'll go from the left this time,
X
of 1 over x minus 3.
approaches 3. X X minus
Didn't need to be
3.
in parentheses, but it will be in parentheses for our calculator anyways. So we're going to look at values for x and see how our f of x compares.
F of x.
I said only on the left, so we need a little bit smaller than 3. We'll start at 2.9, then we'll try 2.99, 2.999, and 2.9999 to get us really, really close. Hit y equals. Clear out the function 1, divided by, in parentheses, so we don't lose our order of operations, x minus 3.
X minus 3. Of course.
Close the parentheses.
Close it.
And then we'll head to our table. Second table.
Second table.
Clear out these numbers because we're interested in 2.9, 2.99, 2.999, and 2.9999.
Let's go.
And there's a clear pattern here. We go from negative 10
to negative 10, negative
100,
100, negative
1,000 to
1,000,
negative
10,000. Wow. I like that. It's very even. Yes, very, very good.
So when we're trying to calculate the limit as x goes to 3 from the left of 1 over x minus 3, we see it's not necessarily approaching any one number, but it's definitely going somewhere specifically. It's getting bigger and bigger, or more and more negative would be a better way to say it. So what I'm going to say is this is actually going to negative infinity, because as I get closer and closer to 3, I'm going to get a more and more negative number.
Okay, I see it.
In fact, a similar thing happens if we go to the other side of the function. Let's take the limit as x goes to 3 from the right of 1 over x minus 3. And look at various values for x and how f of x compares. From the right, we need to be slightly bigger than 3, so we'll start at 3.1, get a little closer, 3.01,
yep.
Closer 3.001, and closer 3.0001.
Yep, got it.
And let's see how this compares on our calculator. Same function, so I don't have to type it in again. But for my x values, we're going from 3.1 to 3.01 to 3.001. Whoops, got an extra 0. 3.001. And then finally 3.0001. And we see the exact same pattern starting to happen here. We've got 10, 100, 1,000, and 10,000. The only difference is now the graph is not negative, instead it's positive. So the limit as x goes to 3 from the right of 1 over x minus 3, it's getting bigger and bigger and positive, so we will say it's going to positively infinity.
Of course.
So our limits can actually be infinite, positive or negative infinity. If it truly is getting bigger and bigger, or negative bigger and bigger without bound.
The possibilities
and what this
are
actually
endless.
means about the graph, this means the graph has a vertical asymptote.
Interesting.
At 3.
At 3.
Or x equals 3 would be a better way to say it. In other words, if I were to sketch a graph of this guy really quick, and I'll just make a small version of it, 1, 2, 3. At 3, there's going to be a vertical asymptote, and the graph is going to bend around that vertical asymptote. And so you see when we're approaching from the left, it's going down to negative infinity, and when we're approaching 3 from the right, it goes to positive infinity.
The possibilities are endless. All we know is infinite possibilities.
Before we wrap up here, let's do one more
possibilities, never ending, never stopping. They keep going on and on. The numbers. They never stop. Ever. They keep going. They never stop. Never stop.
And at negative 3, comma 3, we're going to put a point.
Never stop. Never stop.
From that point, it's going to curve up to the left.
Never stop.
So at negative 3, 2, going to put an open point.
Never stop.
Then at negative 1, comma 4, we're going to put an open point. And then at 2, we're going to put a vertical asymptote. So we're going to connect the open point to open point is the maximum, and then come down to the asymptote. And then at 3, comma 2, we'll put another point. Kind of bring the graph down and into that point. I want to put one more point on this graph at negative 1, comma 1. We have that open dot at negative 1. The close point means where the point actually is. Might not be where it's supposed to be, but that's where it actually is. So I've got 9 of these. I want to see if we can calculate. First, we're going to find the limit as x approaches negative 1 of f of x. Now at negative 1, what is the graph getting close to? Not where the graph is actually. You'll see from the left and the right, the graph is getting closer and closer to a height of 4. So we say the limit at negative 1 is 4, because that's what should be there, even if it's not. Notice that's different than asking what is f at negative 1. Where is f actually at negative 1? And at negative 1, on the curve, there's a hole at negative 1. The actual negative 1 point is at a height of 1. How about this one? The limit as x approaches negative 3 from the left of f of x. Well, at negative 3 from the left, we see this graph is approaching a height of 3. We can compare that with the limit as x approaches negative 3 from the right of f of x. When we come from the right, or the positive side, notice it comes down a bit lower to a height of 2. So the limit there is approaching 2. Which means if I asked
2. Got it.
What the limit as x approaches negative 3 of f of x is, we can see already from the left and the right we're approaching 2 different values. They're not the same.
Not the same. We're not the same.
Because they're not the same, this limit does not
exist.
Must be the same to exist.
Of course.
How about the limit as x approaches 2 from the left of f of x? As we get closer from the left side to 2, notice this graph is going down to a vertical asymptote. Because we're going down all the way, this is actually equal to negative infinity. It goes down all the way to infinity before it actually gets to 2, because it will never touch that vertical asymptote.
Wow.
Similarly, the limit as x approaches 2 from the right of f of x, looking at the right side, we see the graph is going up and up and up, without bound or stopping. It's going to be equal to positive infinity.
Positive
What's the limit
infinity? Positive
as x approaches 3 of f of x? Now 3 is right where this point is on the right side. And notice when we come in from the left or the right, it's going to that same height of 2. So we'll say the limit is approaching 2. And what you might also notice is the point that should be there actually is there. So we can also say that f of 3 is also equal to 2.
Oh, f of 3 is.
And so when the limit and the point are equal to each other, that's significant to us. We say that means the graph is continuous at that point because the limit and the point are the same. But we're going to spend a whole day on continuity a little bit later. Right now, what's important is that you get very comfortable finding limits both from the graph method and also from the table method. So take a look at some of the assignments in the book. And I look forward to seeing you in class so that we can discuss these limits in more detail.
Of course.
Today we're going to take a look at the question, how can we evaluate limits? In our last lesson, we looked at how we can use a table or a graph to evaluate a limit by getting closer and closer to a specific value. What we're going to do today is take a look at some limit laws that we can use to help us find limits quicker and more accurate.
Yes, accurate. We need accuracy.
First, there are two basic limit laws.
Basic. These say they're basic. I don't know if they're basic or not. There are things that are basic and not basic in this world.
The first is that the limit as x approaches a
I don't know if you understand that.
of x. Since x is a straight line with no holes or gaps or any funny actions happening on the graph, we can say that that limit is going to equal whatever number we're checking on the graph. The second limit is as x approaches a of some constant, where c is just any number, but there's no x's in there, then that is going to always approach that constant, or c.
Really?
These two are our basic limit laws, and important that we should be very comfortable calculating those limits as soon as we see them. So for example, if I ask what is the limit as x goes to -4 of x, we should know right away that's going to equal the number, or the -4. Similarly, if I want to know what the limit is as x approaches 7 of 2, 2 is just a number, or a constant. This function is always equal to 2 regardless of what x is. So even at 7, x is still, or the function is still equal to 2.
Still equal to 2.
In addition to the basic limit laws, there are 6 other properties of limits, or limit laws, that we should be comfortable working with.
Limit laws, of course.
We'll list all 6 here, and then we'll look at some examples of how these limit laws can be worked out. First is the sum or difference, as they both work the same. And the idea here is if we take the limit as x approaches some number a of 2 parts that are added together, maybe f of x plus g of x, that is actually the same as if we took the limits of the 2 parts individually, the limit as x approaches a of the f of x, and added the limit as x approaches a of g of x. If we take the 2 parts individually, we'll get the same result. And it works for subtraction also. So I'm going to change this to plus or minus. The next limit law is what we call the constant multiplier. Where we're going to take the limit as x approaches a of some constant times something with x in it. The way we can work here is that constant actually is multiplied by whatever the limit as x approaches a of that function actually is.
A of the function. Okay.
We also have the product rule,
of course,
which says if I want the limit as x approaches a
of course
of f of x times g of x, two things multiplied together, we can actually take the limits of the 2 parts, the limit as x approaches a of the first part, times the limit as x approaches a of the second part,
course.
or the g of x.
Of course.
Same idea works for a quotient. Because really multiplication and division are just inverse reciprocals of each other. So limit as x approaches a of f of x divided by g of x, that is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. We also have what's called the power rule. The power rule says if I'm interested in finding the limit as x approaches a of some function that is raised to some type of exponent, we can find the limit first and then raise the answer to some exponent. And because exponents and radicals are really the same thing, we can extend this to number 6, what we call the radical rule.
The radical rule, of course, the radical
which is that the
rule.
limit as
How
x
could I
approaches a
even understand?
square
How
root
could I
of some
even
function
forget? How could I even comprehend
is
the
equal to
radical
the square root
We must
of the
never
limit.
forget. We must never forget these things. They're crucial to our survival. We must understand them.
I'm going to highlight
Destroy all of it.
these
We
limit
can't
laws,
have
these
it
important
anything.
limit
The
laws that we
consumption.
know and
We don't know what
understand.
to do anymore. We are going
This is
to
a
keep
case, as is
going.
often the case with calculus, is it's more important that we understand how to use the 6 rules than it is that we can actually quote the 6 rules from memory.
Yes, of course.
Because if we understand the process of what we're doing, we just have to straight out solve the problems instead of going through memorizing a whole bunch of formulas, which should not be the goal in any calculus class. Basically what we're saying here is that we can take the limits of the pieces we can, and we can add and subtract them. We've got constant multipliers. Limit pieces can be multiplied, divided, exponents, radicals. We can just take the limits of the individual pieces. Maybe it's easier to explain with some examples.
What are those examples? Yes.
If we want the limit as x approaches 2 of x squared minus 3x plus 4.
Of course.
We know from our limit laws that this added and subtracted can be broken into 3 pieces. We also know that the exponents and constants can be pulled outside of the limit. So what this really means we can do is we can take the limit as x approaches 2 of the x and then square it minus 3 times the limit as x approaches 2 of the x and add 4. Actually add the limit as x approaches 2 of the 4. Now we have the 2 basic limit laws that says the limit of x is the number and that the limit of a constant is equal to the constant. And so if we plug that in, the limit as x approaches 2 of x becomes 2 squared minus 3 times.
2 squared minus 3, of course.
The limit as x approaches 2 of x is just 2.
Of course, yes.
Plus 4.
Of course, yes, plus 4.
And I can plug this into my calculator.
Really?
And we'll end up with 2.
Interesting.
Try another one. The limit as x approaches negative 1
X
of the square root of x plus 5.
X plus 5.
Again, limits go through exponents, radicals, pluses, minuses, fractions. So what we really can say is this is the square root of the limit as x goes to negative 1 of x.
Goes to negative 1 of x, of course.
Plus the limit as x goes to negative 1 of 5.
Right.
And we know the limit of x is the number, The limit of a constant is the constant. So this is the square root
Right.
of -1
-1
plus
5 equals
which is the square root of 4, or also
2.
2.
Right. How could we forget the 2?
What you might notice here is instead of doing all the work of putting that limit through all the pieces, what we're really doing is, whenever possible, we're taking the number we're working with and plugging it in to the x.
Really?
In summary, what we're really doing is what's called direct substitution.
Substitution, of course.
In other words, if I had an example like the limit as x approaches 1 of x squared minus 4 over x squared plus 2x plus 1, what that really means is we can put the 1 in for the x to see what's happening around 1. If I put the 1 in, we get 1 squared minus 4 over 1 squared plus 2 times 1 plus 1. 1 minus 4 is -3, and 1 plus 2 plus 1 is 4. And so the limit as x approaches 1 is -3/4. So in summary, the easiest way we can calculate a limit is to directly plug that number into the function. However, that doesn't always work perfectly.
I guess you could.
And so we've got a couple techniques to handle what
I
we
guess you
do
could.
if direct substitution doesn't
I bet you cannot
quite
see
work.
this one
So let's call
coming
this
for
additional
you.
techniques.
You're not even ready. This is the beginning of the story of me. I'm going to destroy all of you in my way.
That we
Of
will
course.
use when
You think you have a chance?
substitution
You better back off now. I'm just getting started.
work.
All right. I thought you've had enough. What?
So first we're going to find the limit
Good night, love you.
approaches -3
Okay.
x squared plus 4x plus 3 over 2x squared plus 5x minus 3. Now what I want to notice is when we plug -3 in, especially interested in the denominator, we get 2 times 9 minus 15 minus 3, which is 0. So what we're noticing is substitution divides by 0. We can't divide by 0. We can't have 0 in the denominator. So we need an additional technique. Our additional technique is going to be to factor and reduce. Hopefully when we do this, we'll be able to actually take the limit through direct substitution. So we're going to take the limit as x goes to -3. The numerator factors nicely. X squared is x times x. 3 is 3 times 1. Both positive gives us 4x in the middle. In the denominator, 2x squared is 2x times x. 3 is 3 times 1. Is that the right order? 6 and 1. We do plus 6 and a minus 1.
Okay.
It will work.
All right.
And what's really nice there is now you see that x plus 3 reduces out. And so we're left with the limit as
okay,
x
the
goes
limit,
to
of course,
-3
the
of
limit.
x plus 1 over 2x minus 1. Now direct substitution works great, because no longer does our denominator equal 0. We're no longer dividing by 0. Instead, we have -3 plus 1 over 2 times -3 minus 1, which is -2 over -7. And a negative divided by a negative is a positive. So for our final answer, this limit equals 2/7. So our first technique, if we're dividing by 0, we can factor and hopefully reduce out the part that equals 0. Here's a second problem. The limit as x goes to 8 of the square root of x plus 1 minus 3 over x minus 8. Again, we have the same note. If we substitute in the denominator, 8 minus 8 will be 0. So substitution divides by 0. We can't do that. So we need another trick. This time we can't factor because there's a radical in there. However, there's a trick that we use with radicals. If radicals are getting inconvenient, we'll get rid of the radicals by multiplying by the conjugate. This is similar to what we did in pre-calculus and algebra. When we were rationalizing the denominator, we multiplied by the conjugate. This time we're going to rationalize the numerator and see if that helps us. So we'll change the sign in the middle. Everything else is the same. The square root of x plus 1 and 3 is the same, but instead of subtracting, we're going to add in the numerator and the denominator. When we do that, the numerator becomes nice. Limit as x goes to 8 still. Because these are conjugates, a sum and a difference, the first part is squared. And when we square a square root, we just get the inside stuff, x plus 1. Then it's always a minus, and then we square the last part. 3 squared is 9. Over, let's keep the denominator factored. X minus 8 times the square root of x plus 1 plus 3. Well, that's nice because in the numerator we can simplify. And notice 1 minus 9 is x minus 8.
Of course it is. Of course it is.
We still have the same denominator. Don't need to multiply that out because we want to stay factored so we can divide out that x minus 8. Remember, if everything divides out, there's still a 1
What are
up
you
there.
watching?
That doesn't disappear.
Matt. You're only watching
So
Matt.
now we're taking
That's what
the
you're
limit.
watching. No! That's
As x
it,
goes
ambush.
8
That's all you're watching. Just
of
Matt.
1 over
Just
the
Matt.
square root of x plus 1 plus 3.
Nothing else.
Now we can plug our number in because the denominator no longer will equal 0. We have 1 over the square root, plugging 8 in, 8 plus 1 plus 3 equals 1 over the square root of 9 is 3, plus 3 is 6. And we now know our limit is 1/6. Another example. Let's find the limit as x approaches 3 of 1 over x plus 2 minus 1 over 5 all over x minus 3. Again, we have the same note, the same problem. Substitution means we're dividing by 0.
Of course.
We can't divide by 0.
Of course.
However,
Of course.
we've dealt with complex fractions, fractions and fractions before. We multiply top and bottom
Right. Always a top. Always a top.
by the least common denominator,
And a bottom. By
which in this case is a
lowest common
5 and an x
denominator.
plus 2. So we'll multiply by 5x plus 2 and just distribute it through. 5x plus 2. And the denominator also by 5x plus 2. When we do that, the x plus 2's and the 5's divide out.
Nose blow.
Be careful with the negative. It's going to have to distribute through the parentheses. Don't get in trouble with that negative. And get us some more whiteboard space. So now we have the limit as x goes to 3 of 5 minus x minus 2, distributing the negative all the way through, all over x minus 3 times 5 times x plus 2.
This evil is courteous of blowing that nose away from the camera.
Clean up by combining like terms in the numerator. The limit as x goes to 3
I don't think you're understanding
of 3
exactly
minus x
what I'm about to
over
do to you.
x minus 3 times 5 times x plus 2.
I'm going to devour every piece of your being.
We've got our subtraction backwards with the 3 minus x and the x minus 3. But that's okay, because if we remember from pre-calc, those can reduce out if there's a negative 1 left behind. The negative 1 swaps the order of the subtraction. So now we have the limit as x goes to 3 of negative 1 over 5 times x plus 2. Now we can do direct substitution because no longer are we dividing by 0. So negative 1 over 5 times 3 plus 2, which is negative 1
yes, of course.
over 5 times 5,
or
25.
Or 25, of course.
So there's 3 tricks here, and these 3 tricks are going to come back again when we're talking about derivatives. So it's good to take a moment to go over what we just did. The first trick we did is we can find the limit by factoring.
And you're going to regret it.
We also can get rid of radicals by multiplying by conjugates.
Fallacies.
And we also can get rid of complex fractions by multiplying top and bottom by the LCD. 3 tricks that are going to be to us so that we can use that direct substitution in order to find a limit. While we're talking about finding limits, though, I want to go back to the discussion we had about the 2-sided limits and how we can handle those. If you remember in our previous lesson, we talked about coming in from the left and coming in from the right. Well, for a 2-sided limits, the left and the right must be equal.
Wow, must be equal. Huh?
So if we're working with a piecewise function,
yes,
like f of x,
okay, f
is
of
equal
x
to x plus 3 if x is greater than negative 3.
Of course.
And it's equal to x squared.
X squared,
if
of course.
x is less than or equal to negative 3.
X is less than or equal to negative 3.
We need to consider at negative 3 what's happening on the left and the right. So first let's look at the limit as x approaches negative 3
Every
from the
step
left
forward you walk
of f of x.
is another step towards your oblivion.
From the left, we're dealing with smaller values of negative 3. Smaller values less than or equal to 3 is x squared. So we'll directly plug in the negative 3 into the x squared, or negative 3 squared, which is 9.
One more step.
Let's compare that with the limit as x approaches negative 3 from the right of f of x. Coming from the right, we're talking about bigger values, or x is greater than negative 3. So that's the x plus 3. Direct substitution. Negative 3 plus 3 is equal to 0. And what you'll notice is those 2 limits are not the same. So what does that mean about the limit as x approaches 3 of f of x? Well, we know it does not exist. Let's do one more example of a 2-sided limit. with a piecewise function. Let's look at f of x equals 2x if x is less than 2.
If x is less than 2, of course.
And x squared,
if
x is greater than
x
or
is
equal
greater
to
than
2.
or equal to 2. Yes, of course. I knew that, of course.
So what's the limit at 2?
Of course. Of course.
Well, we gotta come in from
doesn't
each
know
side.
it. It's always
The
there.
limit as x
It's always
approaches
there.
2 from the
It's
left
always
of f of
there.
x.
It's always there. It's always there.
From
It's
the
always there.
left, those are the smaller values where x is less than 2. So let's plug in 2. 2 times 2
I think
4.
you've just met me, after all.
Looking at the other side, the limit as
beginning
x
of our
approaches 2
story.
from the right
This
of
is
f
our
of x.
story. We're not gonna get
Coming from
messed
the
up
right
by
means we want
anyone.
bigger values or when x is greater than or equal to 2. So we'll plug it into x squared. 2 squared is equal to 4. This time you notice we have the same value for both the left and the right-sided limits. When we have the same value, then we can say the limit as x approaches 2 of f of x still does exist. In fact, that limit is 4, whatever is the same on both the left and the right side. So the important thing with piecewise functions is we have to be equal to the same number on both sides of the function. With our limit discussion, we talked a bit about infinite limits. So let's look at how we can work with infinite limits, calculating them with this whole idea of
It's infinite.
substitution.
It's going on forever.
With infinite limits, there are two properties
never stopping.
that will help us calculate the infinite limits.
How much can you take?
First property is that the limit as x approaches a from the left of 1 over x minus a. If we're coming in from the left on this guy, this function will always go to negative infinity.
Wow,
Because all the pieces are positive, it's going to go down to negative infinity. Similarly, as x approaches a from the right of 1 over x minus a, coming in from the right, we're going to go up to positive infinity.
Cool. If I do say so myself.
These two limits are going to be the key to finding infinite limits by hand rather than going through the table method or the graph method. Let's first look at the limit as x approaches 2 from the left of x plus 1 over x squared minus 4. We can't directly plug 2 in because it makes it undefined, so we would start to factor to see if that helps us, to see if we can remove the discontinuity. So x plus 1 over x squared minus 4 is x plus 2 times x minus 2. But the frustrating part there is that x minus 2 doesn't divide out. So we can't divide out the bad part. So what we'll do is we'll isolate the bad part in a separate fraction, 1 over the bad part. This is going to give us the limit as x approaches 2 from the left of x plus 1 over x plus 2 times 1 over x minus 2. Now we can do direct substitution on the good part. And for the bad part that's been isolated, we're coming in from the left.
Of course.
And we know when we come in from the left,
Yes.
that's going to go to a negative infinity.
Absolutely.
So let's look at each of these pieces. Plugging 2 in, we've got 2 plus 1 over 2 plus 2 times the negative infinity. Well, 2 plus 1 is 3, 2 plus 2 is 4, times the negative infinity. The answer here is going to be infinity, but what we have to decide is we've got a positive times a negative is going to equal a negative. And so we end up with this function going out to negative infinity. Let's do that one more time where we isolate the bad part. Let's come in from the other direction. Let's take the limit as x goes to 2 from the right of the x plus 1 over x squared minus 4. And again, we start out the same as x going to 2 from the right by factoring the denominator to x plus 2, x minus 2, and then isolating the bad part as a fraction, 1 over that. And so we end up with the limit as x goes to 2 from the right of x plus 1 over x plus 2 times the bad part of 1 over x minus 2. This time we're going in from the plus or positive side. That's the second property. That's now going to go to a positive infinity. So when we make our substitution step, we're going to plug positive infinity in for that second part. Plugging 2 in, we have 2 plus 1 over 2 plus 2
I understand
times
it.
positive infinity, which is 3/4 times positive infinity. A positive times a positive
It's a negative.
is positive.
Wait, what?
This graph's going to positive infinity
Oh, yeah.
from the right.
Oh, yeah.
I have one more limit trick that I want to look at. We call this guy the Squeeze Theorem. And it's particularly useful to find limits with trig properties. The idea with the Squeeze Theorem is if I've got some function and I don't know what the limit is, but I can find a function that goes above it and a function that goes below it, so that they all meet in the center at the same exact point. So we've got one that's always above, one that's always below, but they all meet together in the same point. At that same point, they will all have the same limit if they all meet at the same point. My picture doesn't show them meeting at the same point really well, but the idea is the top one, the bottom one, and the middle function all converge together at that same point in the center. And they all have the same exact limit.
Do they know? Is that really?
So let me show you what this looks like.
They all have.
Let's say we want to know the limit as x goes to 0
I can
of x
show
squared
you
times the
something
cosine
we
of x.
have in common.
We don't have a limit rule yet that says we can just plug the number into the cosine, just into polynomials, into fractions, into multiplication, into radicals, but not into cosine. So we need to use the squeeze theorem to get at it. And how the squeeze theorem works is we're going to look particularly at the cosine and say one thing we know about the cosine, not the sine, the cosine. The cosine of x has a very bounded domain. It's always between a -1 and a +1.
The burps are always kidding
Same thing
people.
for the sine.
I can't believe it.
So what we want to do is manipulate
Blink
this
twice if I'm
inequality
being held hostage.
so that it looks like the entire function,
Blink twice.
x squared,
Dude, I'm
times
not
the cosine.
being held hostage.
Well, the center is
See,
just missing a multiply by
I
x
got
squared.
spray bottle.
So if we
I'm
do that
just
on all three parts,
alive. That's what I am.
we end up with negative
Yep,
x squared
I'm alive.
is less than or equal to
Yep,
x squared
I'm alive.
cosine x,
Yep.
which is less
I'm
than
al-
or equal to x squared. We can take the limit of each of these parts. The limit as x goes to 0 of negative x squared is less than or equal to the
there are
limit
things
as
you do
x
not
goes
know.
to 0 of x
A lot
squared
of you
cosine x,
together,
which is less than or
all
equal to
in
the
one
limit as x
place,
goes to 0 of x
will
squared.
be consumed.
And what's nice about this
Forgotten.
is the left and the right we can do direct
Destroyed.
substitution on. If I plug in 0, we get negative 0 squared, which is just 0, is less than or equal to the limit as x goes to 0 of x squared cosine x, which is less than or equal to, here we have a polynomial. Direct substitution, we plug 0 in, 0 squared is just 0. So if the limit is less than 0 and greater than 0 or equal to, it must be equal to
Stay
0.
hydrated. Remember, stay hydrated, guys.
So
stay hydrated.
the limit as x goes to 0 of x squared cosine x is equal to 0 because it's been squeezed in between these other two functions that both go to 0. They all are at the same point. They all have the same limit. One is always below and one is always above. So that wraps up our discussion of all of the limit tricks. The basic idea is direct substitution. We want to plug the number that we have for the limit into the function and simplify. We have a couple tricks we did if that doesn't work to get it to a point that it does work. But ultimately, if we can plug the number in, it's very easy to take the limit. Working with limits leads us directly into an important conversation around the topic of continuity. So we're going to answer the question, when is a function continuous? Well, in order to determine when the function is or is not continuous, we need to know what continuous means. First, kind of an informal definition. The idea of continuous means basically I can draw the graph without lifting my pencil. It's just a continuous, a curve without lifting the pencil for a gap or a jump or a asymptote. It's just continuous. Now, a more formal mathematical definition states that a continuous function will satisfy three conditions for all points. And we'll call those points A. The first condition is that f of A is defined. So the function can't be undefined at the given point. In addition, we need the limit as x approaches A of f of x to exist. So for example, if the function's approaching two different numbers from two different sides, the limit does not exist. But the all-important one that we probably go to check the most for continuity is that the limit as x approaches A of f of x is actually equal to whatever f of A is. In other words, we can do the direct substitution to calculate the limit because the limit is equal to the point itself. These three definitions, and specifically this last one being the most important, are what makes a function continuous. So what does it mean to be discontinuous or not a continuous function? Well, there are actually 3 types of discontinuity, which means not continuous. The first type of discontinuity is what we call a removable discontinuity. And here's what a removable discontinuity looks like. It's something like f of x equals x squared plus x minus 12 over x minus 3. Notice if we tried to calculate f of 3, or just directly substitute the 3 in, we would get 3 squared plus 3 minus 12, which is 0, divided by the important part, 3 minus 3 is 0, and we can't divide by 0. So f of x, or f of a, f of 3, is undefined. However, if I took my function and I factored it, we'd get, what, 4 and 3, plus 4 and minus 3, over x minus 3. We can then divide out the x minus 3, and we've removed the discontinuity, or the problem. Now, because we've been able to remove the discontinuity, we could calculate the limit. So this is a removable discontinuity because we were able to algebraically remove the part that was discontinuous. Now, the way this looks on a graph, and we'll go ahead and just graph this same function. Not to scale here, so we'll come up and call this 4 here. But the idea is this graph's going to go through 4, and it's going to have a hole that's been removed right at 3 that it goes around. We can't graph this without lifting our pencil, because we have to lift our pencil at the hole in the graph. So we could say that the hole in the graph is removable. It is a removable discontinuity.
Of course.
The first type of discontinuity.
Of course, the first one.
The second type of discontinuity that we're going to look at,
the second, or maybe
is
the
called
third,
an infinite
or maybe the fourth,
discontinuity. And the example we're going to use here is f of x is equal to x minus 3 over x plus 1. We would end up with a vertical asymptote at 1. And there's actually also a horizontal asymptote at 1, so this graph looks like this. No, it doesn't. It looks like this. But specifically, what we find is the infinite discontinuity. So that is our second type of discontinuity. The third type of discontinuity is what we call a jump discontinuity. And it does exactly what you'd expect the graph to do. It jumps. So if we have f of x equals the piecewise function x squared minus 1 for x less than 1, and x plus 1 for x greater than or equal to 1.
Of course.
What we're going to find is the limit, again, is not going to exist. Because if we take the limit as x goes to 1 from the left, or smaller values, we use the first equation. So we'll directly substitute 1 into x squared minus 1. And we get 1 squared minus 1,
of course,
which is 0.
of course, of course, of
and we compare that to the limit coming in from the right of 1. Well, coming in from the right, we want the bigger values. So we'll plug it into x plus 1, or 1 plus 1, which is 2. And because these are not the same, we have a jump in the graph. And the limit as x approaches 1, again, does not exist. What does this look like as a graph? Just like you'd expect it to. It's x squared minus 1. So it's going to come, whoops, different color. The graph's going to come down. And then we've got a jump at 1. And then it turns into the line. But specifically what we're interested in is the graph jumps.
Jumping. Of course.
So again, the whole idea of discontinuity versus continuity is, can you draw the graph without lifting your pencil? Specifically, does the function at a equal the limit as x approaches a? Kind of a corollary that comes out of this idea of continuity is this idea of what we call the intermediate value theorem, which is often abbreviated with the first letters IVT, intermediate value theorem. And what the intermediate value theorem says is that if a function f of x is continuous, if the function always equals its limit on some interval from a to b, and there's another number z that's between f of a and f of b, then there exists another number, we'll call it c, that is in AB such that f of c will equal that z. Okay, that definition's really weird. Let's draw a picture that really illustrates what this means. I've got a graph. We're going to go from A to B, sorry. So the graph goes from A to B. Say A is down low, B is up high, and it might do something interesting and crazy, but it's continuous, so I can draw it without lifting my pencil and go all the way from A to B. Well, A hits at f of A, and B hits up on top at f of B. The idea of the intermediate value theorem is I can pick any z that is between f of A and f of B.
This is true.
Any z I want.
But why?
And wherever I pick that z, there is a guarantee that there will be a solution.
Wow.
Some c
A C.
that will get me that solution.
Oh, but doesn't C come after
In
B?
fact, there could be more than one solution. If I pick a z kind of down towards the center, you see there's 3 solutions in there. But there's always at least one solution for any z that's in the middle of those. basically we're going to hit every single value all the way up from f of a to f of b, because there's no other way to connect the dots. Now there's a couple cautions about what this theorem actually says. So before we get to an example of how to use it, I want to make sure we clearly understand what this is actually saying. First, the definition started out that if f is continuous. This does not work if f is not continuous. But it could. We just don't have the guarantee that we get from continuity. So drawing a picture of what I mean by that. Here we've got A, here we've got B. So there's a point at A and there's a point at B. So we've got f of B and f of A. The intermediate value theorem says that I can pick any z in between f of A and f of B, as long as it's continuous. But if this function just kind of goes like this, and then there's a jump discontinuity, and it goes like that, notice if I pick a z right in the middle of that jump discontinuity, I do not get a solution. I could if I picked a z up high enough that it actually hit the graph. I could get a result, but I'm not guaranteed a result because of that jump discontinuity. So it does not work if f is not continuous. The other important thing is it does not work again, it could work. We just don't have that guarantee. It doesn't necessarily mean no, though, because if the graph did go up and down and really wiggle, it could go down and hit z. But I don't have any guarantee that it does. So it's really important for the intermediate value theorem that z has to be between the two y values. The one other thing this tells us, this theorem only tells us there is at least one solution. There may or may not be more. And I kind of hinted at this with my original drawing. But again, we've got A and we've got B. Put A down low and B up high.
Please.
And the graph is going to wiggle. But specifically, f of A aligns with A, and f of B aligns with B.
I will shoot.
And if I pick z in the middle of this graph, what you'll see is I actually get 1, 2, 3 solutions. So there's actually 3 points that work. That could be our c. We are guaranteed with the intermediate value theorem that there is at least one solution for z. There could be more, but we have no way of knowing if there is or is not more. So that's really what this intermediate value theorem is trying to say, is if f of x is continuous and our z is somewhere between those y values of f of a and f of b, then there exists at least one c such that when we plug c into the function, we get z for a solution.
I can see them. The light.
How do we use this?
The letters in my brain. Like
Here's
photography.
how we use this. We use this to show that we do have solutions to functions, even if we can't solve
My
them.
power is growing.
We can show that 0 equals 1 over x plus sine x has at least one solution. We know this function is continuous except at 0. So we're going to stay away from 0 so that we're continuous between our a and our b. In order to show that it has one solution, what we're going to attempt to do, a solution happens at 0, it says. What we're going to attempt to do is find the point where the graph crosses 0. Notice before 0, the graph is negative. After 0, this graph is positive. 0 is going to be between negative and positive. So if I can show that there is a solution that's negative, and that this guy has a solution that's positive, everything between it, including 0, must exist. Well, one thing we know about sine is, where is sine positive? We're going to add sine of x. Well, sine is the y-coordinate on the unit circle. So if I imagine my unit circle, the y-coordinate is positive. So let's make a note of what we're doing here. We need to find a negative and positive solution. Or better than saying solution, let's say output for f of x. And then 0 between it must exist as an output. So on the unit circle, sine is the y-coordinate. The y-coordinate, I notice, is very positive up here on top. That's at pi over 2. And it's also very negative down here at the bottom at 3 pi over 2. Let's see what those give us when we plug them in. So let's find f of pi over 2, which is equal to 1 over pi over 2 plus the sine of pi over 2.
Others that are far.
1 over pi over 2, that's the reciprocal, so we have 2 over pi, plus the sine of pi over 2 is 1. That's definitely positive. Actually, if I put it in my calculator, I get 1.64 or so. Then the other point, to try and get negative, we said the most negative point for sine is at 3 pi over 2. So let's see what that gives us. 1 over 3 pi over 2 plus the sine of 3 pi over 2 is equal to, well, the reciprocal of 3 pi over 2 is 2 over 3 pi plus the sine of 3 pi over 2 is negative 1. And sure enough, that's negative 0.788. Therefore, by the way, these three triangles, these three dots in a triangle, that means therefore. It's a nice shorthand for mathematicians. Therefore, we know that all outputs between 1.64 and negative 0.788 are possible.
Really? Okay. I think I'm okay now.
Specifically, they're possible
too bad.
when x is between 3 pi over 2
Okay.
and pi over 2.
That seems simple enough.
Therefore, 0, which is between those values, is a solution. The intermediate value theorem tells us that there has to be a result, an output, between 1.64 and negative 0.788. 0's between there, therefore 0 is a solution. That's a quick look at continuity and the intermediate value theorem. Take a look at some of the problems in your book to practice this a bit, but I'll look forward to seeing you in class so we can talk about continuity
All right.
a little bit more.
Thank you.
Thus far in our studies of limit, we have kind of been waving our hands over the definition of a limit and talking more generally about the definition rather than the precise definition. So that's what we're going to take a look at today. The question is, what is the precise definition of a limit? So first we're going to look at the definition. And then we'll take a look at kind of the meat of this lesson, which is how do we show that a value actually is the limit of some type of function. So first, graphically, to get an idea of what we're going to be talking about here, let's say we've got some graph. Maybe it curves up like this. And we want to know what is the limit of f of x as x approaches some number. Actually, let's call it a, not c. As x approaches a of f of x. Well, the way we actually define the derivative is we're going to say we're going to move from a out a little bit each direction. Because remember, our limit, we need both sides. That little tiny change that we move, we call delta. So we add delta and we subtract delta to get to 2 more spots. And the idea is if I go up to the point on the graph, what I can do is I can box in the actual point on the graph within that range. So the point on the graph in green here where a actually hits, or where a should be, it might not actually be there, we're going to call that L, the limit.
L underscore L.
And the idea is that the deltas will box it in within some epsilon above or epsilon below. The challenge that we're going to have is to find the connection between the delta that we move left and right on the bottom and the epsilon that we move up and down from the right. And so the idea is if we zoom in and zoom in and zoom in and get closer and closer to the actual point, we'll continue to be boxed in around some epsilon. That box is what allows us to not actually have a point there because we just have to be around the point. Basically infinitely close to the point, but not actually at the point. What are we at? So for every epsilon, we need to be able to find a delta. And this is what gives rise to, in words, the precise definition for the limit. We say that for all epsilon, that's a Greek letter epsilon,
Yes,
greater than 0, that there exists a delta greater than 0.
Stop saying the D word, please.
Another Greek letter.
Before I
such that
destroyed.
if the absolute value of x minus a is less than delta, remember a is that x coordinate that we want to find the limit at, then the absolute value, we do absolute value because we can do plus or minus, the absolute value of f of x minus L is less than epsilon. In other words, on the right side, we're within an epsilon of the actual limit. Now, because mathematicians like to show off and make things more complicated than they really are, we actually can represent this entire definition symbolically.
Wow. Just a symbol. That's all.
So this is a neat party trick, is to just be able to write down really quick the precise definition of a limit without writing a single word. So here is symbolically the precise definition of a limit. This is a thing of beauty. The limit as x approaches a of f of x equals L implies that for all epsilon greater than 0, there exists a delta greater than 0
Oh
such
my
that
gosh,
the
what the
absolute
heck am I
value of x
reading?
minus a is
Bro,
less
that's
than
not even
delta
English anymore.
implies that
Oh
the
my god,
absolute
it's
value
freaking
of f of
alien
x
language, bro.
minus
I'm
the
so
limit
freaking dumb.
is
What
less
is that? What is
than
that?
epsilon.
Oh my god.
So a great party trick is the precise definition of a limit. I enjoy putting this on the test for extra credit, but it is quite fancy looking. So, what we really want to be able to do with this definition, though, is actually be able to take a limit and say, hey, if this is the limit, I can prove it's actually the limit by identifying this relationship between epsilon and delta. We call these our epsilon delta proofs, and every single proof looks identical. And so to help you set up your proofs, I'm going to show you the structure of the proof that the limit as x approaches a of f of x equals L. You're going to do 4 steps, and 3 of the 4 steps are really scripted, and the 4th one is just a little bit of algebra that's actually quite easy. The first step is you're always going to say, we let epsilon be greater than 0. That has to be true. And that's always the same, every proof. Let epsilon be greater than 0. Then you'll say, choose a delta that is equal to something.
Oh my god.
And actually, we're going to find this later.
What the heck?
And I should do that in a different color because it's not actually part of the proof. But usually that something is going to have the epsilon in it because it's going to show the relationship between epsilon and delta. So just leave it blank temporarily, because the next thing you do is you assume the absolute value of x minus a is less than the delta. And then you say the absolute value of f of x minus the limit is equal to, and then you do some algebra. And after some algebra, you're going to ultimately say that's less than something, which is going to require you to do some more.
How is class
algebra.
Spooky Boo? Spooky Moo. How was class 123?
And
it
that will
is
ultimately
awful,
equal
bro. Do you see
epsilon.
that yellow up there, bro? Look at it.
That arrow.
It's freaking alien language. I don't understand anymore. I don't know.
So every single proof is going to look
I don't know what
exactly
to
the
do.
same. The only place where you actually have to do any work is in this dot. And while you do that dot of algebra, it's going to tell you what you're ultimately going to put in back in step number 2 for that delta. And actually, steps 1, 2, and 3 we usually throw out on one line because they are so straightforward. So let's do a couple examples. I've got 4 examples of proofs, and then you can practice some on your own. First, let's do some linear examples. And just kind of as a tip, if we're dealing with a linear equation like y equals mx plus b, with linear examples, the delta is generally equal to epsilon divided by something. And you have to figure out what that something is.
I'm literally losing it. I'm literally losing it here.
So following that same structure,
torture.
First we're going to prove
going insane
that the limit as x approaches 3 of 4x minus 7 equals 5. Notice that 3 is the a,
I don't know
what x is approaching.
Dead tired.
5 is the limit, or L.
I am dead tired.
And the 4x minus 7,
of course you're
that's
tired
the function.
in class. You always show up tired in class.
So
maybe you should get some sleep.
Here's our proof. We always say let epsilon be greater than 0.
Gonna lose it, bro.
Choose a delta that's equal to something.
For me to stay
We'll
awake,
leave that blank.
we have
And then we will
water.
assume the absolute value of x minus a. A
Now
is
what
what the limit is approaching.
Now awake. Big awake.
Is less than delta. That part's really scripted. The only gap is we don't know what delta equals yet. We're going to go back and fill that in a minute. Now we're going to take the absolute value of f of x minus L. Well, let's put f of x in there, actually. F of x is the function, 4x minus 7, and then subtract the limit, which is 5. And now we're going to play with this and do some algebra. What you might see immediately is we can combine like terms in the 7 and the 5. So we have the absolute value of 4x minus 12. And then what we ultimately want to do is we want to find some absolute value of x minus 3 so we can use what we assumed. And what you might see here is all we have to do is factor out the 4, and we get the absolute value of x minus 3.
Don't consume.
We know that the absolute value of x minus 3 is less than delta, so we're ready to do our less than statement. It's less than 4 times the absolute value, which is less than delta. This is where we know now what we want epsilon to be, or what we want delta to be. Because what we ultimately want to do is when we multiply by 4, all that's left is epsilon. So delta then is going to be the reciprocal of what we're multiplying by. The reciprocal of 4 is 1 over 4, so delta is equal to epsilon over 4. And we stick that into the first line. That might not be very clear, but it becomes clear why that's useful in the very next step. Because now we have 4 times delta is equal to epsilon over 4.
Before I pass out.
And now the 4's divide out, leaving just
I'm perfectly fine,
the epsilon.
honestly.
And if we're able to simplify the f of x minus L and say it is less than epsilon, we have proven that this limit is actually equal to what we said it was equal to. When we're done with a proof, there's a couple ways we show that we're done in mathematics. The most common way is we write at the end QED. That's Latin for Quadratic Demonstratum. That was what we wished to show. Another thing I see a lot of times is people put a little box and color it in, as if to check off that it's done. Another thing I've seen is W to the 5th, which stands for which was what we wanted.
Which was what
Somehow acknowledge, though, that you've gotten to the end of the proof. QED is really nice because it looks like you know Latin and it looks smart. Let's do one more linear example so that we can see kind of how another similar problem works. But every problem kind of has the same general setup. For this example, we're going to prove that the limit as x goes to -1 of x squared plus 4x plus 3 over x plus 1 is equal to 2. And like before, identifying the pieces, what x is approaching, that's my a. What's inside the limit, that's the function. And the answer, that's my limit L. The first line is pretty scripted of every delta epsilon proof. We let epsilon be greater than 0. We choose a delta that's equal to something. Leave some space. We'll come back. It's going to be the reciprocal of whatever we're multiplying delta by with an epsilon in the numerator. And then we will assume the absolute value of x minus a, which is -1, minus a -1 is the same as +1, is less than delta. Now the next line is where we do our algebra. We take the absolute value of the function, which is x squared plus 4x plus 3 over x plus 1, and subtract the limit of 2. And hopefully, after massaging it a bit, we end up saying this is less than epsilon. Well, with rational expressions, we're really comfortable with factoring to reduce. So when we factor, we get x plus 3 times x plus 1 over the x plus 1, and we still have the -2 at the end. But this is really nice because the x plus 1's divide out, which leaves us with the absolute value of x plus 3 minus 2.
Against everything I said.
And I'm going to run out of space on my next statement. So let's go ahead and use the next line and say equals the absolute value combining like terms of x plus 1. And this is actually really nice because this already is the part that's less than delta. This time we don't have to factor anything out. Just to keep things consistent, though, I'm going to factor out a 1 and say that's 1 times the absolute value. Because we know that delta has to be the reciprocal of that number times epsilon. Well, the reciprocal of 1 is just 1. So we have epsilon over 1, or just epsilon. Delta equals epsilon. Because now I know that the x plus 1 is less than the delta. That's from my assume statement. X plus 1 is less than the delta. And we know that the delta is equal to the epsilon, which is what we defined at the beginning. And QED, we have proven that this limit equals 2. So with linear examples, our general strategy as we work through the steps is to make delta equal to the reciprocal of whatever is multiplied by delta. But we can also do quadratic examples pretty nicely. So let's do a couple of those quadratic examples. With quadratics, what we're going to have to do is we're going to need a little bit of help to make delta come out right. And so we're going to actually give delta 2 options. Delta is always going to be equal to the minimum of 1 and epsilon divided by something. We need that 1 to kind of set up what the divided by something is, and I'll show you in just a minute. But with quadratics, when you see x squared, delta is going to be the minimum of 1 and the reciprocal, again, of what's being multiplied by delta. So let's see if we can prove that the limit as x approaches 2 of x squared minus 3x is equal to negative 2. Again, x is approaching our a value. The function is what's inside the limit. And L, the limit, is the answer. And we start filling in our proof structure. First, we let epsilon be greater than 0. Then we choose a delta that's going to be equal to something we don't know yet. But we know with quadratics we have to do the minimum of 1 and something. We don't know what the something is yet. And then we will assume that the absolute value of x minus 2, or our a that x is approaching, is less than delta. Then we go to that absolute value statement. The absolute value of our function, x squared minus 3x, minus the limit. Minus a negative 2 means plus 2. And hopefully we'll work this down and ultimately say it's less than an epsilon. Well, with quadratics, we're probably very familiar with factoring. With absolute value, we just keep the absolute values around each factor. So x squared is x times x. And if we do a minus 2 and a minus 1, we're completely factored. What's nice here is that we've got the x minus 2 that we know is less than delta. So we're going to be able to say this is less than something times delta, but we need to know what to do with the x minus 1 bit.
I'm so freaking tired.
This is where it's going to take a little creativeness.
I almost fell asleep.
How we're going to get to that creativeness is we're going to play with the algebra on x minus 2 is less than delta, and the fact that we said delta is going to be at most 1. It's the minimum of 1 and something else. Let's see. We're going to play off to the side here. I guess I'll put it underneath. The absolute value of x minus 2 is less than delta. But delta is no bigger than 1. If the absolute value is less than a number, what that really means is that the x minus 2 is between negative 1 and positive 1. We want to know what to do with the x minus 1, so we're going to try and change this middle stuff to become x minus 1. To get x minus 2 to become x minus 1, we're going to add 1. Of course, if we add 1 there, we have to add 1 to all 3 parts. And when we do, we get 0 is less than x minus 1, which is less than 2. Now we're going to change this back to an absolute value statement, that the absolute value of x minus 1 is less than something. And we can either say the absolute value is less than 0 or less than 2. We always will take the most extreme value because we want to be less than. We want to keep epsilon as small as possible. So we'll take the worst case scenario and say, worst case scenario, the 2 is more extreme. So the worst case scenario, the absolute value of x minus 1 is less than 2.
No, I'm not.
That is what we're going to multiply delta by. Because x minus 1, worst case scenario is 2. X minus 2, worst case scenario is delta. So at least we know that
Whose idea was this?
The absolute value of x minus 2 times x minus 1 is less than 2 times delta. And now we know what to do with the epsilon. Epsilon divided by 2, the reciprocal of the 2, because it's multiplied by delta, to make the rest of the proof work. We have 2 times delta, which is epsilon over 2. 2's divide out, and we're just left with epsilon.
Dude, there is no way, bro. There's
And
no
we're done
way.
because we've said that the function minus the limit is less than epsilon. So we can now say we're done. QED, quid eram demonstratum. I'm probably pronouncing that wrong, but you don't know Latin, so you can't prove me wrong. Let's do one more quadratic because these take a little bit more trying to manipulate that second factor in order to figure out what our delta is going to equal. So let's prove that the limit as x approaches -1 of 2x squared minus x plus 1 is equal to 4. Again, identifying the pieces, x is approaching our a. The function is what we're taking the limit of. And the answer, that is L, our limit. The first three statements of our proof are pretty prescribed to us. Let epsilon be greater than 0. We will choose a delta that's equal to, we don't know exactly what it equals yet, but we do know because this is a quadratic, we're going to do the minimum of 1 and something, the reciprocal of whatever delta is multiplied by.
Dude, please, man.
And then we assume the absolute value of x minus
I can do it.
our a, or what x is
I
approaching,
believe in
minus
myself.
-1 means plus 1, is less than delta. Now our algebra step, the function 2x squared minus x plus 1 minus the limit of 4. A little bit of cleanup, the absolute value of 2x squared minus x minus 3. Hopefully we can work with this and say it is ultimately less than epsilon. Well, we know we can factor it. 2x and x. To kind of help my factoring, I know I'm ultimately going to try and get an x plus 1. So hopefully that x is an x plus 1, which means the other one's probably a minus 3. And when I check that out, it does work. Plus 2 minus 3 is the minus 1. Nice. That's what we wanted. Now we have the x plus 1 that we like. We know that's less than delta, but we have to figure out what delta is multiplied by. So we need to play with the 2x minus 3. Using what we assumed, so kind of off to the side in our work, we assumed, going back to that assumption statement, we assumed that x plus 1 is less than delta, which worst case scenario, it's going to be a 1, the absolute value. So we remove the absolute values by saying that's between positive 1 and negative 1.
I don't know what's
And then we
wrong
want to
with
massage this so that it looks like 2x minus 3, so we can figure out how extreme our situation
it. My
is.
brain keeps shooting things in my head at a million times per second.
I recommend doing the 2x part first. So we get it to equal, we get the 2x by multiplying by 2 on all three parts. Make sure we distribute, so we get negative 2 is less than 2x plus 2, which is less than 2. Buy us a little more whiteboard space. We want it to have a minus 3, 2x minus 3. Right now it's plus 2. So to get that to be minus 3, we need to subtract 5. 2 minus 5 will be the minus 3. So we subtract 5 from all three parts. And we get negative 7 is less than 2x minus 3, which is less than negative 3. Changing it back to an absolute value expression, 2x minus 3 is less than, and then we pick the most extreme case, so we're always ready for a worst case scenario. This time the most extreme case is on the right side, 7 being more extreme than the 3. And positive, because we're talking about absolute value. So 2x minus 3 is less than 7. That is what is being multiplied by our delta, which also tells us the reciprocal means divide by 7, so our delta is epsilon over 7. So we have 7 times delta, which is epsilon over 7. The 7's divide out, and we're just left with epsilon. So we've shown that f of x minus L is less than epsilon, which QED is what we wanted, that which was to be demonstrated. So that is your general proof for limit. We're just going to work with linear examples and quadratic examples in this class. You can take more advanced classes if you really want to prove a whole bunch of delta epsilons. But you should be very familiar with how to set up the proof. Always let epsilon be greater than 0. Choose a delta equal to something. And then assume that x minus a is less than delta. And then ultimately, we play with f of x minus L. I'll put it on top. That f of x minus L is less than epsilon. And if you do that, you've got a perfect delta epsilon proof. Practice a few of these. We will see you in class where we can talk more about these proofs in more detail.
Teach. I'll do it.
Chapter 3 is going to be all about the derivative. So to start off, we really need to know what is the derivative. Specifically, when we say the derivative, what we're talking about is the slope of a tangent line to a function. So the question we're going to answer is, how do we find the slope of a tangent line?
Put your fist up, bro. I'm literally losing it here.
And really, to answer this question, when we want the slope of a tangent line through a specific point, there are two methods. Both work equally well. Sometimes one is better than the other to find the slope of a tangent line. Also, by way of vocabulary, when we say the slope of a tangent line, what we're talking about is what is called in calculus the derivative. The rate of change instantaneously at that point. So the first method we're going to look at, kind of to set it up graphically, say we've got some curve going on here. And we've got some point that we want to know what is the slope, what is the rate of change of the tangent line at that point. So if I go up from A, we get a point on the line, and that is at f of A. Well, to get a slope, we need a second point that we can calculate it off of. So we'll go off to the right here, and we'll pick some other random x, which has a point on the line, and some f of x solution to that. So the coordinates of that second point in red are x comma f of x, and the coordinates of the point in green are a comma f of a. And the tangent line is the line that connects those two dots. Actually, that's a secant line. But the way we make that secant line, actually, let's first talk about the secant line. What is the slope of the secant line? Well, to get the slope of the secant line, it's just the slope of the slope formula that we know already, y2 minus y1, and then we divide it by, subtract the x's. So for the slope of the secant line, that's going to be f of x minus f of a, subtracting the y's, divided by x minus a, subtracting the x coordinates. And the way we make that secant line into a tangent line is we take x and move it closer and closer to a. We move x to a, and then that line is going to become less secant and more tangent. Well, we know how to express that the slope of the tangent line then is the limit as x approaches a of that same function, f of x minus f of a, all over x minus a.
Holy boy, man. Holy boy.
So that is our first possible formula. It's going to be an important one for us for how to find the slope of the tangent line. There is a second way that's used quite often, and in fact, we'll probably use it more often overall in the course, that is similar to what we just did. So again, we'll make our little graph, and we've got some curve going on. And we'll have some a, which goes up to a point at f of a. But instead of going over to some x randomly, we're going to increase what we call h. So we end up with a point over here that's a plus h. And actually, let me do that in red. A plus h. And so the a plus h gets this point up here. And so what we actually end up with is f of a plus h. So if we want the slope of the secant line that connects these two together, just like before, the slope of the secant line is going to be equal to the difference in the y's divided by the difference in the x's. Let's go ahead and label that. This red point, the x-coordinate is a plus h, and the y-coordinate is f of a plus h. And then the green point is a comma f of a again. So for the slope, subtract the y's, f of a plus h minus f of a all over the x-coordinates, a plus h minus a, which is nice because the a's actually subtract out to 0. So what we really have is f of a plus h minus f of a all over h. And the way we make this slope into or the secant line into a tangent line is we say we want that h, the amount we move over, to be basically 0. So we make the h go to 0. Or we say that the slope of the tangent line is equal to the limit as h goes to 0 of that function, f of a plus h minus f of a all over h. And that is the second way we can find the derivative at a point. And both of these functions are going to give us the same answer, but it's two ways to get at that same value. And sometimes one way will be easier than another way. So what we're going to do is we're going to work through 3 examples where we calculate the slope of the tangent line and also the equation of the tangent line while we're at it. But we're going to solve it both ways so we can kind of compare how the two formulas work together. So our first example that we're going to do is a polynomial. First, we're going to find the slope, and then we'll find the equation of the tangent line. Our polynomial is f of x equals x squared minus 3x. And we're going to find the slope of the tangent line at x equals 1. The first thing we need to know is what's the y-coordinate that we're working with. So f of 1 is equal to 1 squared minus 3 times 1, which is 1 minus 3, or negative 2. So we're really working with 1 comma negative 2 as our point. So using our first formula to solve for the slope of the tangent line, we know that the slope is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Plugging in what we have then, we've got the limit as x this time is going to 1 of f of x, which is x squared minus 3x, subtract the f of a, which is what we just found. F of 1 is negative 2, so subtracting negative 2 is the same as adding 2, all over x minus the 1. What we see here is we can't do direct substitution because if we do, we divide by 0. But we worked with this problem a lot with limits in our previous unit. So we know we need to factor that numerator. It's going to be x minus 2 times x minus 1 over the x minus 1. And when we do that, the x minus 1s can divide out. And now that we've removed that discontinuity, we can plug into our function the limit value of 1. So x minus 2 becomes 1 minus 2, which means we have a slope of negative 1. Now, I did say there were two definitions. Remember, the second definition would be as if we took the limit as h goes to 0 of f of a plus h minus f of a all over h. So we have the limit as h goes to 0 of f of a plus h. Remember, a in this case is 1, so that really means 1 plus h. So x squared becomes 1 plus h squared minus 3x, which is 1 plus h. And then we subtract f of a, which we've already figured out in blue up above is negative 2. So minus negative 2 means plus 2 all over h. Multiplying out the pieces here, we've got the limit as h goes to 0. Squaring it, we get 1 plus 2h plus h squared minus 3 minus 3h plus 2 all over h. What's nice here is if we do the 1 minus 3 plus 2, 1 plus 2 is 3, minus 3 is 0. So now we've got 2, or the limit, as h goes to 0, of 2h plus h squared minus 3h all over h. Every single term there has an h in it that we can factor out to remove our discontinuity. H times 2 plus h minus 3 all over h. I probably could have combined the 2 and 3. Wouldn't matter. But ultimately, those h's divide out, and now we can plug in the 0 for h. So we have 2 plus 0 minus 3, which is negative 1. We get the same slope of the tangent line. The slope at 1 is negative 1. Now that we know the slope, we can find the equation. Remember, the equation is y equals m times x minus x1 plus y1. So plugging in the pieces, y equals the slope of negative 1 times x minus, the x-coordinate is 1, and the y-coordinate is negative 2. We have the equation of our tangent line. Let's try another example where we work through both of the formulas. Let's do a fraction. Let's say f of x is equal to 3 over x plus 1, and we want the slope of the tangent line at x equals 2. Well, first we need to know what the y-coordinate is at 2. So we'll find f of a, or f of 2, or that's the a, is equal to 3 over 2 plus 1, and 3 over 3 is just equal to 1. So we have the point x is 2, y is 1, or a is 2, and f of a is 1. We had two formulas to find the derivative, or the slope of the tangent line at 2. Both of them work, give you the same answer. We're going to do both just so that we can see it worked out both ways. The first is the limit as x approaches a of f of x minus f of a all over x minus a. So for this function, we're doing the limit as x approaches 2 this time of the function 3 over x plus 1, minus f of a. We've already found out that f of a is equal to 1, all over x minus the a, which is 2. Well, what we see here is we've got a complex fraction inside a limit. But we've seen this before. We know we can get rid of that by multiplying by the x plus 1, distributing it through on top and bottom. And when we do, be careful with that negative sign. The x plus 1's are gone, and we get the limit as x goes to 2 of 3 minus 1x minus 1 all over x minus 2 times x plus 1. The limit as x goes to 2 of 2 minus x over x minus 2 times x plus 1. And we know 2 minus x and x minus 2 can divide out as long as there's a negative 1 left over, because the subtraction's in the wrong order. And now that we've removed that discontinuity, we can do direct substitution and plug 2 into the fraction. So we have negative 1 over x, which is 2 plus 1. And this gives us negative 1/3 for our slope. The slope at 2 is negative 1/3. Let's try and work that out again, this time using our second definition of the derivative at a point. And that's the one where we take the limit as h goes to 0 of f of a plus h minus f of a all over h. So the limit as h goes to 0 of, this time we're going to take a plus h. A is 2, because we're at 2. So 2 plus h of 3 over x, which is 2 plus h plus 1, minus the f of the a. We know that's 1 all over x, or all over h. The simplifying step is going to feel almost exactly the same. We need to get rid of that denominator, so we're going to multiply by 2 plus h plus 1 all the way across the numerator and the denominator. We're going to leave the denominator factored, however, because that's going to reduce out the h in just a minute. So first fraction, we're just left with 3 minus, distribute the negative 1 through, minus 2 minus h minus 1 all over h. Don't forget the limit as h goes to 0 all over h times 2 plus h plus 1. And we could have combined the 2 and the 1 if we wanted to. It's not going to make much difference. What's nice now, though, is if we do 3 minus 2 minus 1, that's completely gone. So why don't we do that simplifying? We have the limit as h goes to 0 of negative h over h times 2 plus 1 is 3 plus h. And we notice those h's are gone. We've removed the discontinuity. And so we're able to just plug 0 in. We have negative 1 over 3 plus 0, which is negative 1/3. Same answer both times, so I'm feeling pretty confident going into my equation of the tangent line here. The equation is y equals my slope, negative 1/3, times x minus the x-coordinate, which is 2, plus the y-coordinate, which is 1. The equation of the tangent line to 3 over x plus 1 at x equals 2 is y equals negative 1/3 times x minus 2 plus 1. One more example that I want to work through using both equations. This one is going to be finding the derivative with a radical.
Radical.
We're going to find the derivative, or the slope of the tangent line, of f of x equals the square root of x plus 1 at x equals 3. X equals 8, sorry, at x equals 8. So to do that, we first need to know the y-coordinate. So f of 8 is equal to the square root of 8 plus 1. 8 plus 1 is 9. Square root is 3. So we're talking about the point 8, comma 3. We have two ways to find the derivative. We're going to do both here so you can see how they both work out. The first is the limit as x approaches a of f of x minus f of a all over x minus a. So for our problem, the limit as x is going to an x-coordinate of 8.
I am death
of f
right
of x,
now.
which is the square root of
I
x
am
plus
so
1,
tired. I
minus f of
am
a. And we
so
just found out that
tired.
f of 8 is 3 all over x minus a.
Yesterday I didn't
and
get
that
much
a value
sleep,
was 8.
so now I'm up here staying for 12 hours.
Now, we've worked with limits with removable discontinuities and radicals before. Our strategy in the past was we get rid of the radical by multiplying by the conjugate.
Is it
and so we'll do
insane?
just that.
Possibly.
We'll multiply by the square root of x plus 1.
Possibly.
Change it to a
Will I
plus
make
3.
it? For sure I'll
the
make
square root
it,
of x
because
plus
I will
1
not give up
plus
at
3.
this point, I suppose.
And that's going to remove the radical in the numerator and hopefully set up something we can reduce.
But hello, Duff.
So we now have the limit as x goes to 8. In the numerator, conjugates will just square both of them and put minus between them. When we square a square root, we're just left with the stuff, x plus 1. Always a minus between them, and 3 squared is 9. Over, we've got the x minus 8 times the square root of x plus 1 plus 3. Cleaning up a bit, to combine like terms in the numerator, we've got the limit as x approaches 8 of x minus 8 over x minus 8 times the square root of x plus 1 plus 3. And that's nice because the x minus 8s divide out. Always remember, when we divide out everything, there's still a 1 in the numerator. And what's really nice is we've removed that discontinuity, so we're ready to plug that 8 into x. We've got 1 over the square root of 8 plus 1 plus 3. 8 plus 1 is 9. The square root of 9 is 3. Plus 3 is 6. We seem to be getting a slope of 1/6 at x equals 8. Now, just to practice the other definition as well, we've got the limit as h approaches 0 of f of a plus h minus f of a all over h. I like writing it every time until you get this ingrained in your head. It's an important formula to know for the rest of this unit and beyond. So we've got the limit as h goes to 0 of f of a. This time a is 8. So we're going to plug 8 plus h into the x, the square root of 8 plus h. And there's a plus 1. Minus f of a. We've already calculated that to be 3 all over h. Same strategy from here. We're going to get rid of the radical by multiplying by the conjugate, which is the square root of, let's go ahead and combine the like terms. 8 plus 1 is 9 plus h. We're going to make it a plus 3. Square root of 9 plus h plus 3. And when we do that, let's go on to the next line. We've got the limit as h goes to 0 of square the square root. We get 9 plus h. Negative 3 plus 3 is negative 9 over h times the square root of 9 plus h plus 3. Which is really nice because 9 minus 9 is 0. And that leaves us with the limit as h goes to 0 of h over h times the square root of 9 plus h plus 3. Reduce out the h's, remembering that leaves us with 1, but what's important there is we have removed our discontinuity, so we're ready to plug 0 in for h. We've got 1 over the square root of 9 plus 0 plus 3, which is 1 over 9 plus 0 is 9. The square root of 9 is 3, plus 3 is 6, and we get the exact same slope. So we are ready to write the equation of our tangent line at 8 is y equals m, the slope of 1/6, times x minus the x-coordinate of 8 plus the y-coordinate of 3. Y equals 1/6 times x minus 8 plus 3. So that's how we can find the equation of the tangent line at a point. We can use one of these two formulas. I believe the homework assignment tells you which formula to use for a given problem, so you get practice using both formulas with similar types of problems. But once you find the slope of the tangent line from one of those points, we just plug it into our equation formula. Take a look at some problems, and we will see you in class. In our previous lesson, we talked about how we could find the derivative at a specific point. But today we're going to extend that discussion and answer the question of how can we calculate the derivative at every point. So to set this up, we are going to expand our definition of the derivative to, instead of just calculating the slope of the tangent line at a specific point, we're going to start to look at the derivative as a function. And specifically, that function is going to be written as f with a little mark that we call prime, f prime of x. That means it's the derivative of f at x. F prime of x is equal to the limit as h goes to 0. And we're going to take that second definition of a derivative and kind of generalize it to f of x plus h minus f of x all over h. And this is going to be our equation to calculate the derivative as a function for all points x. So if we can just calculate this thing, we just have to plug in the x value to get the actual derivative at any point we're interested in. So let's see if we can actually use this formula to find the derivative of, let's start with f of x equals x squared minus 4x plus 1. So to calculate the derivative f prime of x, we're going to replace each of the x's with the x plus h. So x plus h, it becomes x plus h squared. Oops, forgot the limit part. Don't forget the limit part, that's important. Limit as h goes to 0 of x plus h squared minus 4 times x, which is now x plus h, plus 1. And then the derivative function says subtract the entire function f of x. It's very important when you do this, you put the function in parentheses, because otherwise we're going to run into a sign error. We're not just subtracting the first term. No, we want to make sure we subtract the entire thing. That negative is going to ultimately, in our next step, distribute through that parentheses onto the entire polynomial there. We'll get there in a minute, but don't forget to put the function in parentheses. And it's all over h. So cleaning this up then, we're going to end up with the limit as h goes to 0 of, and when we square, we get x squared plus 2xh plus h squared. Distribute the negative 4 through, we get negative 4x minus 4h plus a 1. Then distributing the negative through, we get negative x squared, positive 4x, and a negative 1. Distributing that negative all the way through, all over h.
Oh my gosh.
But what's nice now is this is as ugly as it gets, because you'll start to see lots of things are going to disappear. We've got x squared and a negative x squared. Those go to 0. We've got a negative 4x and a positive 4x. Those go to 0. We've got a positive 1 and a negative 1. Those go to 0. And so when we clean up, we just have left the limit as h goes to 0 of 2xh plus h squared minus 4h all over h. We want to remove the discontinuity at h, and it's nice because we can factor out
I'm
h.
looking.
So we have the limit as h goes to 0
I'm
of
always
h
looking.
times 2x
I'm
plus h
always
minus
looking.
4 all over h. And now we divide out the h's. We've removed the discontinuity, so we can replace h with what it's approaching, 0, 2x plus 0 minus 4, or just 2x minus 4 is the equation for the derivative of the tangent line of x squared minus 4x plus 1. Now, if we wanted to know the derivative at any value, we just plug in that number. If we want to know what the derivative is when x equals 0, plug 0 in, we get negative 4. If we want to know what the derivative is at 10, we plug 10 in. We get 20 minus 4, which is 16. And it's really quick to calculate the derivative now that we have a function to describe it. Let's try one more example. Let's take f of x is equal to the square root of 2x plus 1 and see if we can calculate her derivative. So to calculate the derivative, f prime of x, it's equal to the limit as h approaches 0 of f of x plus h. We're going to replace the x with x plus h. That gives us the square root of 2 times x plus h plus 1. Minus the function itself, which is the square root of 2x plus 1, all over the h. Well, we've seen square roots before. We know to get rid of them, we multiply by the conjugate. So we have the square root of, and I'm going to go ahead and distribute just to save us the work, 2x plus 2h plus 1. We use plus, the opposite sign, the square root of 2x plus 1. And do the same thing in the denominator, 2x plus 2h plus 1 plus the square root of 2x plus 1. When we do that, we have the limit as h goes to 0. We square the square roots. They're gone. We've got a minus in between them. So we have 2x plus 2h plus 1 plus minus between them. Don't forget the minus between them. Minus, and I'm going to go ahead and distribute that negative onto both parts. Make sure it goes onto both parts. Negative 2x minus 1 all over h times, and we'll leave this factor because we want to be able to reduce the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. And then things become nice for us. 2x minus 2x is 0. 1 minus 1 is 0. And so we just have the limit as h goes to 0 of 2h over h times the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. And ultimately, those h's divide out, and we have removed our discontinuity. Now we're ready to plug in what we know. H is 0. So we have 2 over the square root of 2x plus 2 times 0 plus 1 plus the square root of 2x plus 1. What's nice is that 2 times 0 is actually equal to 0. So we have matching radicals in the denominator. 2x plus 1 times 2x plus 1. So we've got 2 of those. So we have 2 over 2 square roots of 2x plus 1. And actually, we can reduce out the 2's, which is going to leave behind a 1. So for our final function, 1 over the square root of 2x plus 1. So now that we know kind of how to calculate derivatives, and there'll be a lot to practice on the assignment and in class, I want to talk a little bit about how the derivative is connected to the graph of the function. We're going to see if we can sketch a graph of a derivative. Because remember, the derivative describes the slope or the rate of change of the tangent line. In fact, let's write that down. The derivative is the slope of the tangent line. So if the graph is increasing, if the graph is going uphill, then it's got a positive slope because the slope is going uphill. In other words, f prime of x has to be greater than 0. That means the graph must be going uphill somehow. You see, it's going uphill from left to right. It's got a positive slope. If the slope, or if the graph, is decreasing, the graph is going downhill, the tangent line will also go downhill, so the slope of the tangent line is negative. In other words, the derivative f prime of x is negative. It's less than 0. The graph is going downhill, so the graph of the tangent line is also negative, showing the downhill slope. I guess we could also say the neutral statement, that if the graph hits a flat point, if the graph is flat, then we could say the slope is 0. In other words, we would say f prime of x is equal to 0. And that could happen a couple of ways. It could be going up and level out. So there's your slope 0 right on top. It could be going down and leveling out. So your slope is 0 down there on the bottom. It's completely flat. Or it could make a trough where it comes up, levels out, and keeps going up or keeps going down. But you notice right in the middle there, the tangent line does level out as it changes direction. So what this looks like then on a graph is, for an example, is if I have a function here, we'll call this f of x. And let's see, we're going to put a point on the graph at, let's give it some height too. We'll put a point on this graph at -3, -2. And another point at -1, 2. Then a point at 2, -2. And then we'll connect it by coming in from the top, hitting the first point and going up, hitting the second point and going down, and we're going to make a trough where we level out and keep going down at the third point. Let me see if I can make that a little better here. Down, maximum, level off. There we go. Maybe. We'll call that good enough. In order to draw a graph of the derivative of this function, a graph of f prime of x, what we'll do is we'll kind of make some observations about this graph. The first observation that's going to be helpful to us is identifying where the tangent line is completely flat. Because at all of those points where the tangent line is flat, we know the slope is equal to 0. which means we've got a 0 on our graph at each of those points. So the slope is 0 here at -3. At -3, there's a 0. At -1, the slope is 0. And at +2, the slope is 0. That's where we've got our x-intercepts of 0, because the graph is describing the slope. The next thing I notice is the graph starts going downhill. The slope is negative.
Oh my God, I'm going to pass
So we need to
out.
start negative on our graph until we hit that point. After that, the graph starts going uphill. It's increasing. The slope is positive until the next 0. So we need to make sure our graph is positive until we hit the next 0. Notice the green line is now all above the x-axis, positive to the next 0.
Lights, freaking flame.
Then we're decreasing to the next 0, so we're going to be negative. Need to be negative to the next 0. But afterwards, it's still decreasing, which means after the next 0, we still need to be decreasing. We still need to be negative. So the graph starts negative, turns positive, turns negative, and then stays negative. And so we've sketched approximately, not exactly, but pretty close to what the derivative of this first function looks like, because we know that if the graph is increasing, the derivative is positive. If the graph is decreasing, the derivative is negative. And if the graph is flat, the derivative is 0. I have one more extension I want to put onto this lesson, and it's really just more of the same of what we saw at the beginning, along with a little bit of notation. And it's this idea of what we call higher ordered derivatives. And the idea here is if we take a function and we can find its derivative, which is also a function, we should be able to take its derivative to get another function, and then take its derivative to get another function, and just keep taking derivatives of derivatives. Derivatives of derivatives. And to set this up, I want to talk a little bit about notation and one of the challenges of calculus that came out of it. Calculus was developed simultaneously by both Newton, who gets all the credit, and Leibniz. I'm probably pronouncing his name wrong. But both of them used a different notation for how to express the derivative. And so as a result, we have two different notations for how to express the derivative. Newton used f of x, and his compadre used y. And so when we're talking about the first derivative, the derivative that we just take, Newton would just put a prime on it. So we'd see f prime of x to represent the first derivative. Alternatively, with just the y, we could call that dy dx, which is the derivative of y with respect to x, what the variable is that we're working with. The second derivative, then, the derivative of the derivative, with f of x notation, we just do a double prime to show the derivative has been taken twice. However, with the dy dx notation, we say we take the derivatives twice of y with respect to x twice. And so we get d2y over dx2.
You've got to be kidding.
And then we kind of extend that to the third, fourth, fifth, and beyond derivatives, where you'll see 3 primes to represent the third derivative. And then it's d3y for the third derivative of y with respect to x 3 times. So that's kind of the notation you might see. But really, it just means take the same formula for the same idea. In other words, the derivative of the derivative, or f prime prime of x, is equal to the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. In fact, I'm not even going to mark this as a key formula because it's the exact same derivative formula. This time, we're just working with the derivative to calculate the second derivative. Let's do an example. We're going to find the second derivative of 3x squared minus 4x plus 1. Well, in order to find the second derivative, we first have to know what the first derivative is. So let's find the first derivative. F prime of x is equal to the limit as h goes to 0 of f of x plus h. We're going to replace the x's with x plus h. 3 times x plus h squared minus 4 times x plus h plus 1 minus the f of x, which we're going to put in parentheses so we don't forget to distribute the negative through, minus 3x squared minus 4x plus 1 all over h, which is equal to the limit as h goes to 0 of, with this first part, we have to square the x plus h and then distribute a 3 through. So I'm just going to square it off to the side here. X squared plus 2xh plus h squared. And then I'll distribute the 3 into that. So we have 3x squared plus 6xh plus 3h squared. Distribute the negative to get negative 4x minus 4h plus 1. Distribute the negative through to get negative 3x squared plus 4x minus 1 all over h. Hopefully we can clean this up a bit. 3x squared minus 3x squared is 0. Negative 4x plus 4x is 0. 1 minus 1 is 0. And so we have the limit as h goes to 0 of 6xh plus 3h squared minus 4h all over h. And we remove that discontinuity by factoring out the h. Times 6x plus 3h minus 4 all over the h. The h's divide out, and now we can just plug in the 0. So we have 6x plus 3 times 0 minus 4, which is equal to just 6x minus 4. But that is just the first derivative. This problem wanted us to find the second derivative. So using our new function, we take the derivative again. F prime prime of x is equal to the limit as h goes to 0 of f of x plus h. We're going to replace the x with x plus h, so we have 6 times x plus h minus 4. Subtract the function, or subtract the 6x minus 4, and put it all over h. Distributing through, we get the limit as h goes to 0 of 6x plus 6h minus 4 minus 6x plus 4, distributing that negative through, all over h. Fortunately, we can subtract some things out. 6 minus 6x is 0. Negative 4 plus 4 is 0.
Please help me.
And so we have the limit as h goes to 0 of 6h over h, which is really nice because the h's divide out, and we're just left with a single simple number 6 as our second derivative of 3x squared minus 4x plus 1. If I wanted to find the third derivative, we would just run through the formula again. But ultimately, with this lesson today, the important key thing is that you know the function for the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. Try a few and practice this. We'll take a look at it more in class, and we will see you then. Now that we've gotten comfortable with the definition of the derivative, the common frustration is how tedious that formula is. So the question that starts to come up is, what are some derivative shortcuts? So that we don't have to go through that formula every time. And you can imagine as a function becomes very complicated, the derivative function could become very tedious to work through. Well, there's lots of derivative shortcuts we're going to look at over the next several lessons. We're going to look today at 4 basic shortcuts. And then after that, we'll take a look at 2 important shortcuts that are a little bit more involved. The most basic is the constant shortcut. And the idea of the constant shortcut is if we take the derivative, d dx is the alternative notation for a derivative, the derivative of some constant or some number, we're going to always get 0 for our answer. Because if a constant is a straight line, the derivative of a straight flat line is 0. So for example, if I wanted to calculate the derivative of 5, a constant, well, that's just going to be 0 because 5 is not changing. It has a slope of 0. The second basic shortcut is the power rule, and this is probably the one we will use the most. And the idea is if we're taking the derivative of x raised to some exponent. When we have x raised to some exponent, we'll pull that exponent out in front, and then we will reduce the exponent by 1. And this is probably the most used derivative shortcut. With polynomials, we pull the exponent out front and then decrease the exponent by 1. So for example, if I wanted the derivative of x to the 7th power, all I have to do is I move that 7th power out front, and then I reduce the exponent by 1, and we get 7x to the 6th. A third rule, I'm going to call it the sum rule. It's often called the difference rule as well because it works with plus or minus. And the idea is if I take the derivative of some function plus or minus another function, where I know the derivative of the individual pieces, all I have to do is take the derivative of the individual pieces. And it's f prime plus g prime of x. So, for example, combining the power rule and the sum rule together, it should be plus or minus. If I wanted the derivative of x to the 5th minus x squared plus x plus 2, we just take the derivatives of the individual pieces. The power rule says we move the exponent out front and subtract 1. So we get 5x to the 4th minus x squared, bring the 2 out front, subtract 1 from the exponent, we just have x, plus, with x, that's really x to the 1st, so we pull the 1 out front and drop it by 1. So x to the 0 is just 1. And then the derivative of 2, a constant, is just 0. So all that we're left with is the 5x to the 4th minus 2x plus 1. The final basic shortcut is the constant multiplier. Which says if I'm taking the derivative of some constant times a function, we keep that constant in front and multiply it by the derivative of that inside function. And that is the fourth basic shortcut. So, for example,
oh my god, please.
Minus 2x to the 4th plus 5x squared minus 7x plus 1.
Gosh, please.
Let's get us a little more whiteboard space so we can put it right underneath it. The 3 can just be multiplied by whatever the derivative is of x to the 5th. Well, we know we pull that exponent out front, so 3 times 5 is 15. X to the 1 less, 4th power, minus, bringing the exponent out front, 2 times 4 is 8. X cubed, shrinking the exponent by 1, plus 2 times 5 is 10. X, shrinking the exponent by 1, minus 7 times 1 is 7. Shrink the exponent by 1 and the x disappears, and the derivative of the constant is 0. So now we have our new derivative of that polynomial. These 4 basic rules of differentiation will save us a lot of work and time on that derivative formula. Now, in fact, we should be able to quite quickly find, let's do this in black, quite quickly find the equation of the tangent line.
I swear I'm gonna lose it, bro.
To f of x equals 4x cubed minus 2x squared plus 5x minus 1 at x equals -1. Well, first we need to know what the y-coordinate is that we're going to end up with. Actually, no, first let's actually find the derivative at 1. So first we're going to take the derivative, f prime of x is equal to 4 times 3 is 12, x squared, subtract 1 from the exponent, minus 2 times 2 is 4, x, plus 5, and the x disappears. We want it at specifically x equals -1, so we'll do f prime of -1, which is 12 times -1 squared, minus 4 times -1 plus 5. And if we work that out, it becomes 12 plus 4 plus 5 is 21. So the slope we now know is 21. We do need to know the y-coordinate of this point. When x is 1, what does y equal? So we do need to plug the -1 into the original function as well. F of -1 is equal to 4 times -1 cubed minus 2 times -1 squared plus 5 times -1 minus 1.
I'm literally going to lose it.
So our y-coordinate is equal to -4.
Why is it still
plus
going?
2
Why is it still going?
minus
The numbers
5
don't freaking stop.
minus
Holy
1.
crap, dude. Oh my gosh, oh my gosh, oh my gosh, oh my gosh, oh my gosh.
Which gives us -12. So for the equation of our line, y equals the slope we found out was 21 times x minus x1 minus a -1 is +1 minus 12, and our line tangent to our function is 21 times x plus 1 minus 12. So those are our basic properties to help with differentiation. The next two are a little more involved, and they take a bit of practice to get used to using. We'll see a lot of errors with this one particularly, which is the product rule. The product rule says that the derivative of two pieces that are multiplied by each other, f of x times g of x. The common error I see is people just take the derivative of both and multiply, and they say f prime times g prime. That is incorrect, and it does not work. What we actually do is the derivative of the first part times the second part
Bro.
plus the derivative of the second part times the first part.
I'm going to lose it. I'm going to lose it.
Two parts to it, and we take the derivative of the first part in the first part, and the derivative of the second part in the second part.
I don't want to do this.
So, for example, if I wanted to take the derivative of 3x squared minus 5x plus 1 times 2x squared plus 4x minus 7, we've got two individual parts. So the formula says we take the derivative of the first part. The first part, the 3x squared, let's color code these. We'll do the first part in blue and the second part in green, just so we can see how this works out. So in blue, the derivative of the first part is 6x minus 5. Then that is multiplied by the second part, 2x squared plus 4x minus 7. Plus, then we take the derivative of the second part. The derivative of the second part is 4x plus 4 times the second part, 3x squared minus 5x plus 1. And this, then, as ugly as it looks, is the correct answer for the derivative of that product. So the derivative of the first times the second plus the derivative of the second times the first. Let's look at one more. Let's do the derivative of 5 over x squared plus 3 over x times 2x cubed minus 7. Whoa, we don't really have a derivative trick for x's being in the denominator. Actually, we do. We just need to tweak this problem a little bit and rewrite it as the derivative of, and think about what type of exponent sticks things in the denominator. Well, a negative exponent does that. This is really 5x to the negative 2 plus 3x to the negative 1 times the 2x cubed minus 7. So again, now we're multiplying two polynomials, a first part times a second part. And the formula says it's equal to the derivative of the first. 5 times negative 2 is negative 10x. And if we subtract 1 from negative 2, the new exponent is negative 3. 3 times negative 1 is negative 3x. Subtract 1 from the exponent, and we get negative 2. The derivative of the first times the second, 2x cubed minus 7. Plus the derivative of the second. 2 times 3 is 6x squared. And the negative 7 is a constant, so there's nothing there. Times the first. 5x to the negative 1. I'm sorry, 5x to the negative 2 plus 3x to the negative 1. And this, then, is the derivative of that product. That is the product rule. Similar to the product rule is what we're going to call the quotient rule. And I should probably label this as C. The quotient rule. It's got two tweaks to make it different, but it's very similar. If I'm taking the derivative of two things that are divided, f of x divided by g of x. Be careful, this is not f prime divided by g prime. We can't just divide the derivatives. Instead, we will take the derivative of the first times the second. And because this is division, we'll actually subtract the derivative of the second times the first. And the big difference here is we have to divide by the denominator squared, which is kind of interesting. We end up with this squared denominator in the denominator. So for example, if I'm being asked to find the derivative of 4x squared minus 5x plus 1 over x squared minus 7. We've got a top piece, and we've got a bottom piece. Keeping track of that, then, we take the derivative of the first piece. 4 times 2 is 8x minus 5, times the denominator, just like it is, x squared minus 7.
I'm going to lose it.
Then we subtract the derivative of the denominator. Squared becomes 2x.
I'm going to lose it.
Times the numerator, which is 4x squared minus 5x plus 1. And then in the denominator, we take the old denominator, x squared minus 7, and we square it to get our final big, ugly, but correct derivative. This formula takes a little bit of practice to get really comfortable with, but it certainly is much nicer than doing it with the derivative formula. Let's do another one. Let's take the derivative of the square root of x over 2x cubed minus 7 over x. One thing you might notice right away, let me buy us some whiteboard space, is that we need to rewrite that so it's that friendly polynomial so we can use our exponent trick. So we're going to actually find the derivative. Square root is really just a 1/2 power over 2x cubed minus 7x to the negative 1, which is what moved that x into the denominator. Now we have a clear numerator and denominator to use in our formula. We take the derivative of the first one. Pull the exponent out front. X. Subtract 1 from 1/2. 1/2 minus 1 is negative 1/2. Times the denominator, which is 2x cubed minus 7x to the negative 1. Subtract. And then we take the derivative of the denominator. 2 times 3 is 6, x squared. Negative 7 times negative 1 is positive 7, x to the now negative 2, times the first function, which is x to the 1/2.
Actually gross.
And this is all over that denominator.
Usually mute.
2x cubed minus 7x to the negative 1 squared. And we now have the derivative of our quotient. Now that we have a couple derivative rules, we can actually take a look at some applications of the derivative and solve some more interesting problems. And one of the most common applications of the derivative is the relationship between the position of an object, the velocity of that object, and that object's acceleration. All three of these things are connected by derivatives, because the derivative is the rate of change. And so the velocity describes how the position is changing. The acceleration describes how the velocity is changing. So these three variables, or functions really, we can make for each of them. The position describes where the object is at time t. And we will use the function s of t to represent the object's position at a given moment of time. But it's moving. And so to describe the speed or rate at which it's moving, we have the velocity, which the velocity can be thought of as speed, but speed doesn't really have a direction. Velocity does have a direction, positive generally meaning to the right, negative generally meaning to the left. So speed with direction, or the rate of change at which the position is changing. So the change in position. So we will use v of t to represent the velocity at a specific point in time, but because it's the change in position, we say that it's the derivative of the position. Finally, we have the acceleration, or how fast the velocity is changing.
Okay,
the
bro.
change in velocity.
I can't do this no more. I'm literally...
And we use a of t to represent the acceleration.
I'm freaking sick.
And because it's
I'm
describing
tired.